They did not simply live and die, they bled, they suffered, they fought through agony that would have broken any creature without the raw, primal will to survive. The world of the Mesozoic era was not the cinematic paradise of lush greenery and peaceful giants that we sometimes imagine when we close our eyes and drift back 160 million years. It was a crucible. A grinding, unrelenting engine of violence, disease, infection, and catastrophe that tested every living thing that dared to breathe beneath those ancient skies. And the dinosaurs, those magnificent, terrifying, endlessly fascinating animals, were tested harder than almost anything else that has ever walked this earth. What you are about to witness over the course of this documentary is not simply a collection of fossil discoveries. It is something far more profound than that. It is the reconstruction of individual lives. Real animals, with real injuries, real suffering, and real stories of survival and eventual death, preserved in stone across tens of millions of years, waiting patiently for us to find them, study them, and finally understand what they went through. Every crack in a bone, every healed lesion, every parasitic channel bored through ancient tissue, these are not merely scientific data points. They are biographical details. They are the preserved echoes of pain, of struggle, of moments so intense and so defining that the very skeleton of the animal recorded them permanently, like nature's own black box recorder. Modern paleontology has evolved in ways that would have seemed almost miraculous to the scientists of even 50 years ago. We are no longer simply digging up bones and arranging them into museum poses. We are scanning fossils with computed tomography machines, running isotopic analyses, comparing pathological bone growth against modern veterinary databases, and reconstructing the biochemistry of animals that have been extinct for 66 million years. We are reading medical histories from stone. And what those histories tell us is extraordinary. They tell us that dinosaurs got cancer. They got parasitic infections. They broke bones, healed them, and broke them again. They fought each other with a ferocity that left permanent scars across their skulls. They died slowly from infections that spread through their blood. They died suddenly, buried alive under collapsing sediment, while still performing the most tender acts of parental care. They escaped the jaws of the most powerful predators that ever lived, only to spend months afterward carrying a fragment of a predator's tooth embedded in their own flesh. These are not myths. These are not dramatizations invented for entertainment. Every single case that we are going to examine in this documentary is grounded in peer-reviewed scientific research, in CT scans and histological analysis and comparative anatomy and careful, painstaking fossil preparation that sometimes takes years of delicate work before the full story of a single animal's life and death can be read from the evidence preserved in its bones. The scientists who uncovered these stories are some of the most meticulous and dedicated researchers working in any field today, and the fossils they have studied are among the most remarkable objects that have ever been pulled from the ground anywhere on this planet. Please let us know in the comments where you are watching this video and what time you are watching it. And be sure to subscribe to the channel for future videos, because what we are covering today is only the beginning of a much larger story about the hidden lives of the most iconic animals in the history of life on Earth. We begin with a skull. Not just any skull, but one of the largest, most complete, and most dramatically damaged skulls ever recovered from any ceratopsian dinosaur in the entire fossil record. A skull that tells the story of a giant who survived something that should have killed him, who lived for months with a wound that would have been agonizing beyond our ability to fully comprehend, and who ultimately lost his fight against an enemy so small that it cannot even be seen with the naked eye. An enemy not of tooth and claw, but of the microscopic world, bacteria, spreading silently through his blood, consuming him from the inside as surely as any predator could have. His name, the name given to him by the researchers and fossil enthusiasts who fell in love with his story, is Big John. The year was 2014. In the Hell Creek Formation of South Dakota, a formation of rock that has become one of the most famous fossil-bearing geological units anywhere on Earth, a rancher discovered fragmentary bones protruding from the ancient sediment. The Hell Creek Formation dates to the very end of the Cretaceous period, approximately 66 million years ago, which means that whatever animal left its bones in that rock was living at one of the most dramatic moments in the history of life. In the final chapter of the Age of Dinosaurs, just before the catastrophic extinction event that would wipe out the non-avian dinosaurs entirely. The bones were reported to paleontologists, excavation began, and what emerged over the following weeks and months was staggering in its scale and its completeness. Big John was a Triceratops horridus. That name, Triceratops, is one of the most recognizable words in the English language, embedded so deeply in popular culture that even very young children know what it means. A massive herbivorous dinosaur with 3 horns and an enormous bony frill extending from the back of its skull. But recognizing the name and truly understanding the animal are very different things, and Big John demands to be truly understood, because his fossil is not simply a spectacular specimen of a well-known species. It is a document. A record of violence, survival, infection, and death that illuminates the social behavior and physical vulnerability of one of the most powerful herbivores that ever lived. Big John's skull measures approximately 2.5 meters in length, roughly 8 feet from the tip of his nasal horn to the back of his frill. To put that in perspective, that is longer than most automobiles. His frill alone, that great curved shield of bone that extended behind his head, was enormous, and it is on this frill that the central mystery and tragedy of his life is written in permanent, unmistakable evidence. There is a hole in the frill. But it is not just any hole, not the kind of accidental damage that sometimes occurs to fossils during the millions of years they spend compressed within rock. This hole has a very specific, very deliberate shape. Researchers who examined it carefully, running their eyes and their instruments over its edges and its margins, recognized immediately that its morphology, its shape and its characteristics, was consistent with a penetrating wound inflicted by a horn. Specifically, a horn shaped very much like the horns of another Triceratops. The hole is roughly oval, with a distinctive elongated profile that forensic paleontologists described as resembling the shape of a keyhole. It penetrates completely through the bone of the frill, which means that whatever made this wound drove through solid bone with enough force to punch a clean opening in what was essentially a slab of dense, mineralized tissue. The margins of the hole are not random or fragmented in the way that post-mortem damage tends to look. They are smooth in certain areas, and they show specific patterns of bone displacement that are consistent with an impact wound rather than a crushing or gnawing injury. Everything about this hole points to a single, catastrophic event, a horn strike from another Triceratops, delivered with tremendous force, that penetrated the frill cleanly. Now, the frill of a Triceratops is not simply a passive defensive structure. For decades, the scientific understanding of ceratopsian frills was dominated by the idea that they functioned primarily as shields, bony armor that protected the neck and shoulders of these animals from the attacks of predators. And while that function was probably real to some degree, modern research has increasingly emphasized another role for the frill: display and intraspecific communication. The frill was likely brightly colored in life, possibly with elaborate patterns, and it was almost certainly used in visual signaling between members of the same species, for mate attraction, for dominance displays, for the establishment of social hierarchies. And the evidence from fossils like Big John suggests something even more dramatic, that Triceratops sometimes engaged in direct physical combat with each other, using their horns as weapons in battles for territory, mates, or social status. This was not a small skirmish. This was not two animals gently locking horns in a ritualized display. The wound in Big John's frill represents a massive, driving blow from a horn that was, by any measure, a lethal weapon. The attacker, another Triceratops, presumably a rival male, drove its horn through Big John's frill from behind or from the side, penetrating bone that is several centimeters thick. The force required to do this was enormous. The pain inflicted would have been immediate, searing, and catastrophic. But here is where the story becomes something truly remarkable, something that elevates Big John from a fascinating fossil to a profound portrait of animal resilience. He did not die from that blow. He survived it. And we know this not merely as an assumption or a guess, but because the bone itself tells us so in direct, physical, irrefutable terms. Around the edges of the wound, researchers identified evidence of bone remodeling, the biological process by which living bone responds to damage by generating new tissue, reshaping the injury site, attempting to repair and stabilize what has been broken. This process does not happen instantaneously. Bone remodeling is slow work, carried out by specialized cells called osteoclasts and osteoblasts that work in coordinated teams to first remove damaged tissue and then lay down new bone matrix. The amount of remodeling visible around the edges of Big John's wound told researchers something critically important. This animal lived for a substantial period of time after receiving this injury. The research team, led by scientists from the University of Bologna and other institutions, estimated, based on the degree of bone remodeling observed, that Big John survived his wound for approximately 6 months. 6 months. Imagine what that means. Imagine the reality of being a creature the size of a large rhinoceros, actually significantly larger than a rhinoceros, because an adult Triceratops likely weighed somewhere between 6 and 12 tons, carrying a hole in your head the size of a fist, for 6 months, in an environment filled with predators, disease vectors, and the constant physical demands of finding enough food and water to fuel a body of that enormous mass. The wound would have been open initially, which means it would have been a vector for infection. And this brings us to the element of Big John's story that is perhaps the most medically fascinating, and also the most tragic. The bone remodeling around the wound shows specific patterns that suggest the healing process was complicated. The tissue is not healing cleanly in the way that a simple, uncomplicated injury would. There are signs of periosteal reaction, an inflammation and abnormal growth of the membrane that covers bone, that suggests the presence of infection. The body was fighting something. The wound, despite healing at its edges, was harboring bacteria. The researchers who published the formal analysis of Big John's wound in the journal Scientific Reports described the pathological bone changes in careful, measured scientific language, but the picture they painted was clear. Big John likely developed osteomyelitis, a bone infection, as a direct result of his wound. Osteomyelitis is a condition in which bacteria colonize bone tissue, destroying it and triggering an intense inflammatory response that causes severe, chronic pain. In modern animals, osteomyelitis of this severity, if untreated, which of course Big John could not have received treatment, typically results in systemic sepsis, meaning the infection spreads from the local site through the bloodstream and eventually overwhelms the entire body's ability to function. Big John, in all probability, survived a vicious horn attack from one of his own kind, endured 6 months of worsening bone infection and increasingly severe systemic illness, and ultimately died not from violence but from bacteria. Not from a predator's jaws or claws, but from the invisible microscopic world that colonized his wound and consumed him slowly, inexorably, while he continued to try to live his life in the final, catastrophic period of the age of dinosaurs. What does this tell us? It tells us several things of profound importance. It tells us that Triceratops engaged in genuine, dangerous physical combat with each other, combat severe enough to inflict penetrating wounds through bone. This aligns with the broader pattern that has been observed across ceratopsian fossils, where a significant proportion of frills and cranial bones show damage consistent with intraspecific combat, but Big John's case is among the most dramatic and most clearly documented. It tells us that these animals were physiologically robust enough to survive injuries that would instantly kill most organisms, that their immune systems and healing mechanisms were powerful enough to allow bone remodeling to begin even on a wound of this severity. And it tells us that infection was a real and serious threat in the Mesozoic world, one that could turn a survivable physical injury into a terminal illness, even for the most massive and powerful herbivores on the planet. There is something almost unbearable about the image of Big John in his final months. An animal of extraordinary size and power, an animal that had presumably survived decades of life in one of the most dangerous environments in Earth's history, brought low at the end not by something dramatic and cinematic but by the slow, grinding advance of microscopic organisms through his bloodstream. His skull, preserved in such extraordinary detail, speaks to us across 66 million years with a voice that is somehow both alien and deeply recognizable. He was a living creature. He suffered. He tried to survive. And eventually, like all living things, he succumbed. Big John was purchased at auction in 2021 for approximately $7.7 million, a record price for a Triceratops specimen at the time of sale. He now resides in a private collection, though the scientific study of his remains has been published and is available to researchers worldwide. His skull continues to be one of the most studied and analyzed ceratopsian specimens in the world, and each new examination seems to reveal additional details about the life and death of this extraordinary individual. But as remarkable as Big John's story is, it represents only one way that a dinosaur's life could be defined and ultimately ended by pathology, by the physical breakdown of a living body under the assault of injury and infection. There are other stories embedded in other fossils, stories that point to different kinds of suffering, different kinds of disease, and different ways that the biological machinery of these ancient animals could fail them in the end. And to find the next of these stories, we need to travel not to South Dakota, but to a very different part of the world. To South America. To the sun-baked badlands of the interior of Brazil. Where, in the rocks of the late Cretaceous, a titanosaur left behind bones that contain a secret that paleontologists had never encountered before in any dinosaur specimen, a secret that speaks of parasites, of blood, of bone-deep infection, and of a slow and agonizing decline that transformed one of the largest animals ever to walk the earth into a creature too weak, too damaged, and too sick to continue. The word titanosaur encompasses one of the most diverse and widespread groups of dinosaurs that ever existed. These were the great sauropods of the Cretaceous period, the long-necked, pillar-legged, small-headed giants that represent the apex of vertebrate body size on land. While the famous sauropods of the Jurassic period, animals like Brachiosaurus and Diplodocus, are perhaps more immediately recognizable to general audiences, the titanosaurs that evolved from their lineage and dominated the Cretaceous period were, in many ways, even more extreme. Some titanosaurs reach lengths of 30 meters or more and weights that paleontologists estimate in the range of 50 to 70 metric tons, body masses that dwarf anything else in the history of land animals, that push up against what engineers and biologists calculate as the theoretical limits of what bone and muscle and lung capacity can support against the constant pull of gravity. Brazil, during the late Cretaceous period, was a very different place from what it is today. The climate was warmer, the geography was different, and the faunal communities that inhabited the region were distinct from anything found in the northern landmasses that had once been connected to South America but were by this point increasingly isolated by the movement of tectonic plates. The titanosaurs of South America evolved in relative isolation, diversifying into an extraordinary array of forms, and the fossils they left behind in the rock formations of countries like Brazil and Argentina have been transforming our understanding of sauropod biology for decades. The specimen at the center of this particular story was discovered in the northwestern region of the state of São Paulo, in rock formations dating to the late Cretaceous period, roughly 80 to 90 million years ago. The find was made by researchers affiliated with Brazilian paleontological institutions, and the initial excavation produced a partial skeleton that was, by the standards of Brazilian Titanosaur discoveries, reasonably well preserved. But it was not the gross morphology of the specimen, not its size or its shape, or the arrangement of its bones, that made this particular animal extraordinary. It was what was found when researchers began examining the microscopic structure of the bone tissue under high-powered analysis. Inside the bone, within the vascular channels, the tiny tubes and spaces within bone tissue that, in life, carry blood vessels, nerves, and other biological structures, researchers found something that stopped them cold. Something that had never been seen before in any dinosaur specimen, anywhere in the world, in the entire history of the science of paleontology. They found evidence of hemoparasites. To understand what this means and why it is so significant, we need to briefly step into the world of parasitology. Hemoparasites are parasitic organisms, typically single-celled microorganisms, that live within the blood of their host. The most famous and medically consequential group of hemoparasites in the modern world are the Plasmodium species, the parasites that cause malaria in humans and other animals. But malaria is just one example of a much broader phenomenon. Blood parasites, organisms that infect the red blood cells or the plasma of vertebrate hosts, feeding on their resources, disrupting their physiology, and causing a wide range of pathological conditions, are extraordinarily common in the modern natural world. Birds, reptiles, amphibians, mammals, virtually every major group of vertebrates has its associated community of blood parasites, transmitted by vectors like mosquitoes, biting flies, and other blood-feeding invertebrates. The discovery of evidence for blood parasites in a Cretaceous titanosaur represents a remarkable window into the parasitological world of the Mesozoic. It tells us that the ancient ecosystem of the Cretaceous included not just the large, dramatic animals we know from their skeletal remains, but also a complex invisible ecology of microorganisms that infected those animals, lived within their blood, and shaped their health and physiology in ways that have been almost completely invisible to paleontology until now. But the parasites themselves are not the whole story. Not even close. The story becomes truly tragic when we examine what those parasites did to the bone. Within the vascular channels of the titanosaur's bones, researchers identify not only the structural signatures of hemoparasitic infection but also evidence of a devastating secondary complication, osteomyelitis. The same bone infection that ultimately killed Big John, brought on in his case by a puncture wound, was present in this titanosaur as well. But in this animal's case, the infection appears to have been seeded not by physical trauma but by the parasitic infestation itself. This makes biological sense. When blood parasites colonize the vascular system of a large vertebrate, they compromise multiple aspects of immune function. They consume resources, they trigger inflammatory responses that can themselves cause tissue damage, and they disrupt the normal protective barriers that prevent bacteria from colonizing tissues that would otherwise be defended. A titanosaur with a severe hemoparasitic infection would have been immunologically vulnerable in ways that a healthy animal would not, and the bacteria that are always present in any living environment, normally held at bay by a functioning immune system, could have seized on that vulnerability to establish themselves in the bone tissue, beginning the process of osteomyelitic destruction. The bone pathology observed in this specimen is described by the researchers as acute osteomyelitis. The word acute in medical terminology means rapid, severe, and intense, as opposed to chronic, which describes a condition that develops gradually over a long period of time. The combination of hemoparasitic infection and acute osteomyelitis represents a catastrophic health crisis for any animal, let alone one with the specific biological challenges of a titanosaur. Consider the physical reality of being a titanosaur with osteomyelitis. These animals moved on 4 massive pillar-like limbs, carrying a body weight of potentially dozens of tons. Every movement required the limbs to bear enormous compressive loads. Bone infected with osteomyelitis becomes structurally compromised. It is not simply a matter of pain, though the pain would have been severe, but of mechanical integrity. Infected bone is weaker, less able to bear the forces that normal bone resists without difficulty. For an animal as massive as a titanosaur, even a modest reduction in the structural integrity of a limb bone could be catastrophic. The risk of pathological fracture, a bone breaking not because of external trauma but because the bone itself has been so compromised by infection that it can no longer bear normal loads, would have been significant. The researchers who studied this specimen proposed that the hemoparasitic infection, combined with the secondary osteomyelitis, likely caused progressive deterioration in the animal's ability to move. Chronic pain, structural weakness in the affected limbs, and the systemic effects of a serious infection, fever, metabolic disruption, immune suppression, would have combined to reduce this titanosaur's mobility progressively over time. And for an animal that needs to move substantial distances to find enough food to fuel its enormous metabolism, reduced mobility is not merely an inconvenience. It is a death sentence. A titanosaur that cannot walk freely cannot forage effectively. An animal that cannot forage effectively begins to lose body condition, its fat reserves are depleted, its muscle mass decreases, its metabolic systems are placed under increasing stress. This creates a vicious cycle. The declining health makes the animal less able to find food, which makes the health decline faster, which makes foraging even more difficult, until eventually the animal reaches a point from which there is no return. It becomes too weak to sustain itself, and it dies. This process, driven initially by parasites smaller than a single human cell, led to the death of one of the largest creatures ever to walk the surface of the earth. There is something philosophically staggering about that reality. The architecture of a titanosaur, the massive bones, the enormous muscles, the extraordinary cardiovascular and respiratory systems required to keep a body of that size functioning, represents millions of years of evolutionary refinement toward the goal of survival on the grandest scale imaginable. And yet, all of that magnificence could be undone by organisms so small that they would be invisible not just to the naked eye but to any eye that has not been augmented by the considerable magnifying power of a modern microscope. The discovery of hemoparasitic infection in this Brazilian titanosaur opens up an entire new dimension of Mesozoic biology that has barely been explored. If one titanosaur had blood parasites, then the probability is high that many dinosaurs did, that the ancient ecosystems of the Mesozoic included complex parasitological communities that we are only beginning to recognize and document. The blood-sucking insects and other invertebrates that would have served as vectors for these parasites were certainly present in the Mesozoic, preserved in extraordinary detail in amber deposits from the period. We have fossil mosquitoes. We have fossil midges and biting flies. We have known for years that the biological infrastructure for hemoparasitism existed in the Mesozoic world. But until this Brazilian titanosaur, we had not had direct evidence of the parasites themselves affecting a specific dinosaur individual in a way that we could document pathologically. The full implications of this discovery are still being worked out by researchers. It suggests that the health ecology of Mesozoic dinosaurs was far more complex than the bones alone can show, that disease and parasitism were forces shaping the lives and deaths of these animals in ways that have been almost completely invisible to traditional paleontological methods. It raises questions about how common such infections were, about which dinosaur species were most vulnerable, about whether different groups of dinosaurs had different suites of parasites, and about how the evolution of the immune systems of dinosaurs and their descendants, birds, was shaped by this long history of parasitic challenge. It also, on a more intimate and personal level, gives us a portrait of an animal in profound suffering. A titanosaur, one of the evolutionary pinnacles of vertebrate body size, an animal armored by sheer mass against almost any external threat, slowly brought down by the invisible world. Moving more and more slowly through the Cretaceous landscape of what is now Brazil. Struggling to reach the vegetation it needed. Growing thinner, weaker, more desperate. Until one day it could not rise at all, and the world of the Cretaceous continued around its vast, still body as if it had never been. The bone remembers. Even when the flesh is gone, even when the teeth and the claws and the parasites themselves have long since dissolved back into the chemistry of the earth, the bone remembers in its microscopic structure the story of what happened. And when scientists trained in the reading of that microscopic language examine it with the right tools and the right questions, the bone speaks. Across 85 million years, give or take, it speaks. And what it says, in this case, is a story of infection, of pain, of the slow failure of one of the largest bodies ever assembled by the process of evolution. From the gentle giants of the sauropod world, we now pivot sharply to something very different. Something faster, more aggressive, and armed with one of the most formidable sets of jaws in the history of life. We move from prey to predator. From the quiet, grinding suffering of a creature whose only weapon against the world was its sheer mass, to the violent, dynamic world of a large theropod dinosaur, a predator that hunted, that fought, that dominated its ecosystem, and that shows us, through its bones, that the life of a predator in the Mesozoic was every bit as dangerous and every bit as painful as the life of the prey it hunted. The province of Alberta, in what is now Western Canada, is one of the most productive fossil localities on Earth. The Badlands of Alberta, carved by millions of years of erosion into a landscape of spectacular, almost otherworldly beauty, expose rock formations of Cretaceous age that have been yielding extraordinary dinosaur fossils for well over a century. The Horseshoe Canyon Formation and the Two Medicine Formation, among others, have produced some of the most important dinosaur specimens ever found, and it is from the geological context of this region that the third story in our documentary emerges. Daspletosaurus was a large tyrannosaurid, a close relative of the famous Tyrannosaurus rex, living somewhat earlier in the Cretaceous period, approximately 75 to 77 million years ago. It was a massive animal by any objective standard, roughly 8 to 9 meters in length, weighing perhaps 2.5 to 3 metric tons, bipedal like all tyrannosaurids, with the characteristic massive skull, powerful jaws lined with thick, bone-crushing teeth, and the trademark tiny forelimbs that have made the tyrannosaurid body plan one of the most recognizable silhouettes in natural history. Daspletosaurus was not quite the size of Tyrannosaurus rex, that iconic species, which lived approximately 10 million years after Daspletosaurus, was significantly larger, but it was a formidable predator in its own right, one of the apex predators of its particular time and place in the Cretaceous world of what is now North America. The specimen that concerns us here, the Daspletosaurus individual that tells this particular story, was discovered in Alberta and has been the subject of detailed pathological analysis by researchers attempting to understand not just the anatomy of the animal but the story of its life and death. And that story, as the bones reveal it, is one of extraordinary violence, unexpected survival, and a final end that illuminates the scavenging behavior of Mesozoic ecosystems. The skull of this Daspletosaurus individual displays something that stopped researchers cold when they examined it carefully. There are bite marks on the cranial bones. Not just any bite marks, not the random post-mortem tooth impressions that are sometimes found on fossil bones when scavengers have worked over a carcass after death. These bite marks are healed. The bone around them shows clear evidence of biological response, of periosteal reaction, of new bone formation, of the healing process that only occurs in living tissue. Which means these bite marks were inflicted while the animal was alive. This Daspletosaurus was bitten on the head while it was still breathing. The geometry of the bite marks, the spacing and morphology of the tooth impressions, tells us something about the identity of the attacker. The marks are consistent with the dentition of another large tyrannosaurid, which, given the fauna of late Cretaceous Alberta, almost certainly means another Daspletosaurus. This predator was attacked on the head by a member of its own species. And it survived that attack, at least initially, because the bone healed. The implications of this finding ripple outward into some of the deepest and most contested questions in theropod dinosaur biology. Were large tyrannosaurids social animals? Did they live in groups, perhaps family units or loose associations, in the way that some modern apex predators like lions do? Or did they live largely solitary lives, coming together only for mating, with territorial aggression between individuals being the primary mode of intraspecific interaction? The evidence of healed bite marks on the cranial bones of tyrannosaurids has been accumulating over the years, from multiple specimens, suggesting that facial biting between individuals of the same species was not a rare or aberrant behavior, but something that happened regularly enough to leave a substantial record in the fossil bones of these animals. This is not gentle social bonding behavior. Biting another animal on the skull, particularly when both participants have jaws capable of crushing bone, is extreme, dangerous, potentially lethal combat. Whatever social or ecological pressure was driving it must have been intense. Territory and access to food in an environment where large prey animals were abundant but perhaps not unlimited would have created real incentives for aggressive competition between individuals. Mate competition, particularly if Daspletosaurus exhibited the kind of tournament-style sexual selection seen in many modern large animals, would also have created conditions for serious physical combat. Whatever the cause, this particular Daspletosaurus received bite wounds severe enough to leave clear marks on bone, survived long enough for those wounds to begin healing, and then died, from what cause we cannot determine with certainty. But the death was followed by something that has left its own distinctive signature in the fossil record. The remains of this Daspletosaurus were consumed by another animal after its death. And the bite marks left on the bones by this post-mortem feeding are quite different from the healed antemortem wounds described above. They are not healed, they do not show biological response, they are the traces of teeth working over dead bone. The identity of the post-mortem consumer is, again, suggested by the morphology of the bite marks. And again, the evidence points toward a large tyrannosaurid. Which raises one of the most fascinating and unsettling behavioral questions in the study of Mesozoic predators. Did Daspletosaurus eat its own dead? Did tyrannosaurids practice cannibalism? This is not, it should be noted, an unprecedented or even particularly unusual behavior in the animal kingdom. Cannibalism has been documented in an astonishing range of modern animals, from insects to fish to birds to mammals, typically occurring in conditions of food stress, during territorial disputes, or as a straightforward opportunistic response to an available food resource. A dead Daspletosaurus would represent an enormous amount of protein and fat, a caloric resource that, in the Cretaceous landscape, another predator would have strong incentive to exploit regardless of the species' identity of the carcass. The scenario suggested by the fossil evidence is both biologically coherent and hauntingly dramatic. A Daspletosaurus individual, perhaps weakened by its earlier injuries, perhaps simply old, perhaps killed by some cause unrelated to the intraspecific conflict that left marks on its skull, dies in the Cretaceous landscape of what is now Alberta. And before the decomposition and the sediment burial that will eventually preserve it as a fossil can do their work, another large predator, possibly the same individual that bit it during life, possibly a completely different animal drawn by the scent of the carcass, arrives and feeds on the remains. This image, a massive theropod feeding on the body of another massive theropod, is not the kind of thing that typically appears in popular depictions of dinosaurs. The cinematic dinosaur world tends to be one of clear divisions: predators hunting prey, herbivores fleeing carnivores, a simplified ecosystem of hunter and hunted. The reality revealed by careful paleontological analysis is much more complex, much more brutal, and in many ways much more familiar, because the patterns of intraspecific aggression, territorial combat, and opportunistic cannibalism that appear in the Daspletosaurus fossil record are patterns that appear throughout the animal kingdom. Patterns that reflect the fundamental competitive logic of natural selection in environments where resources are limited and survival requires every possible advantage. The Daspletosaurus of Alberta lived a hard life. It was a predator, yes, a supreme predator, one of the most powerful carnivores of its time and place. But it lived in a world where even the supreme predator was not safe from violence, where even the top of the food chain could be bitten, wounded, infected, and ultimately consumed. The fossil record does not allow us to know the exact sequence of events that defined this animal's end. We cannot be certain of the cause of death, of the identity of the scavenger, of the social context of the intraspecific aggression. But the bones tell us enough. They tell us that this animal fought, that it was hurt, that it healed from that hurt at least partially, and that it ultimately died in a world where nothing, not even the most powerful predator, was simply safe. Now we make a dramatic shift in scale, in biology, and in the nature of the story being told. From the violence and predation of Tyrannosaurid Alberta, we travel across the world to the rolling landscapes of what is now Central Asia, to Mongolia, specifically, to the region around Ukatalgad in the Gobi Desert, one of the most astonishing fossil localities on Earth. This is a place where the ancient sediments have preserved not just the bones of Cretaceous animals but sometimes entire behavioral moments, snapshots of what animals were doing in the instant before death overtook them, preserved with a fidelity and completeness that seems almost miraculous. The Gobi Desert localities of Mongolia have been producing spectacular dinosaur fossils for nearly a century, since the famous American Museum of Natural History expeditions of the early 1920s first revealed to the world the extraordinary paleontological richness of this remote and austere landscape. But it was in the 1990s and early 2000s that a series of discoveries were made in this region that transformed our understanding of dinosaur behavior in ways that went far beyond simple anatomy and taxonomy. These were discoveries not just of bones but of behavior, of posture, of the preserved record of what an animal was doing in its last moments of life. The specimen that concerns us here belongs to an oviraptorid, a member of the family Oviraptoridae, the feathered, beaked, short-faced theropod dinosaurs that have become one of the most iconic groups of Cretaceous Asian dinosaurs in both scientific and popular understanding. The name, oviraptor, is famously and somewhat unfortunately derived from the Latin for egg thief. a name applied to the first specimen of the genus Oviraptor when it was discovered in the 1920s lying near a nest of eggs that were then incorrectly assumed to belong to a different dinosaur. Decades later, further discoveries revealed the truth. The oviraptorids found near nests were not stealing the eggs. They were tending them. They were parents, sitting on or near their own nests, in a posture of protective care that is strikingly similar to the brooding behavior of modern birds. The specimen from Jangi, the one that gives this section of our story its focal point, takes this understanding of oviraptorid parental behavior to an entirely new and heartbreaking level. This individual was not simply found near a nest. It was found on the nest, in an unmistakable brooding posture, with its body positioned directly over a clutch of eggs, its arms extended outward and downward in a wingspread posture that in birds is associated with active thermoregulation of a nest, shading the eggs from heat, or warming them against cold, depending on conditions. And it had been buried alive. The sediment that engulfed this animal and preserved it in such extraordinary detail is interpreted by geologists as the product of a rapid, catastrophic depositional event, almost certainly a collapsing sand dune or a violent sandstorm that buried the animal so quickly that it had no time to flee, no opportunity to escape. The animal died in the position in which it was buried, and the position in which it was buried was the position of an animal engaged in parental care. This is one of the most emotionally resonant fossils ever discovered. The science is clear, the evidence is detailed, and the interpretation is robust. This is not a case of wishful anthropomorphization, but a genuine biological reality preserved in stone. This oviraptorid was doing what it did when disaster struck. It was sitting on its eggs. It was protecting its nest. And when the sand came, fast, overwhelming, inescapable, it did not run. It could not run, or chose not to run, or was buried too quickly to run. It died in the act of parenting. The brooding posture itself is remarkable in what it reveals about oviraptorid behavior and biology. The positioning of the arms, extended outward from the body and curving downward toward the edges of the nest, is consistent with an animal that possessed substantial wing feathers. Feathers that could be used to create a physical barrier around the nest, shielding the eggs from environmental extremes, concealing them from potential predators, and maintaining the thermal conditions necessary for successful incubation. While oviraptorids were not capable of flight in the way that modern birds are, the feathered arms that they likely possessed served real biological functions in the context of nesting behavior, and this fossil provides one of the most direct pieces of evidence for that connection between feathered arms and parental care in non-avian dinosaurs. The eggs in the clutch are preserved as well, arranged in a circular pattern in the characteristic oviraptorid nesting style, laid in a ring, standing upright or at an angle in the sediment, with the adult positioned at the center or slightly off-center of the ring in a posture that allowed maximum physical contact with the maximum number of eggs. This arrangement is not random. It is a highly structured behavior that reflects sophisticated instinctive programming around the requirements of successful incubation. What was this animal experiencing in the moments before its death? This is a question that science cannot fully answer, and perhaps should not try to answer with too much confidence, because the inner lives of non-avian dinosaurs are not something we have direct access to. But we can make some observations. The instinct to remain on the nest in the face of environmental disturbance, to hold position even as sand began to pour over the landscape, is not something we would expect from an animal operating purely on the basis of self-preservation. Even if we resist the temptation to attribute conscious deliberation or emotional response to this animal, the fact that it maintained its brooding posture until it was buried suggests that the neurological drive to protect the nest was extraordinarily powerful. Powerful enough to override, or simply not quick enough to be overridden by, the danger signals that a collapsing sand dune would have generated. The oviraptorid of Jangi died doing what evolution had shaped its brain and body to do. It was protecting the next generation, the eggs that represented its reproductive investment, its genetic legacy, its biological imperative. In doing so, it sacrificed itself to the geological violence of an ancient landscape, and in doing so, it was preserved with such perfection that we can read the story of its death in extraordinary detail 66 million years later. This fossil sits in the tradition of a small number of truly extraordinary paleontological specimens that preserve behavior rather than just anatomy: the fighting dinosaurs of Mongolia, the brooding pseudopody specimens from Ukatalgad, the many Chinese feathered dinosaurs preserved in volcanic ash with their plumage intact. Each of these specimens is a gift of extraordinary specificity, a window into the living world of the Mesozoic that the bones alone, stripped of context and position and association, could never provide. The Oviraptorid of Jangi is among the most complete and most behaviorally informative of these behavioral fossils, and what it tells us about the parental investments of dinosaurs, about the deep evolutionary roots of avian nesting behavior, and about the capacity of ancient animals for what we can at least functionally call devoted parenting, is both scientifically important and genuinely moving. Death by burial. Death without violence, without predation, without infection or parasites or intraspecific aggression. Just the earth itself, suddenly and catastrophically, claiming this animal, while it was engaged in the most fundamentally reproductive act of its life. The rock that killed it also preserved it. The sediment that smothered it also froze it in time. And what it preserved, what it froze, was a moment of parental devotion that speaks across the vast gulf of geological time to something that feels, against all the scientific caution we can muster, deeply and fundamentally recognizable. From Mongolia and the story of parental sacrifice, we return now to the northern landmass, specifically to the geological formations of the western interior, where in the late Cretaceous period a massive, diverse community of dinosaurs inhabited the floodplains, forests, and river systems of a continent that was, at that time, divided by a great interior seaway into western and eastern landmasses. It is from this world, warmer than today, more humid in many regions, dominated by the sounds of hadrosaur herds and the distant crashing of large theropods through the vegetation, that our next story emerges. And this story is, in some ways, the most personal of all the cases we are examining today. Because it is a story about a single animal and a single predator, about a moment of violence and a miraculous escape, and about the long, painful aftermath of that escape, a period of months during which a hadrosaur lived with a piece of its predator permanently embedded in its own body. The hadrosaurs, commonly called duck-billed dinosaurs for the broad, flattened rostrum that characterizes their facial anatomy, were among the most successful and widespread of all Cretaceous dinosaurs. They were large herbivores, typically ranging from 7 to 15 meters in length depending on the species, and they formed a dominant component of the late Cretaceous terrestrial ecosystems of the northern hemisphere. They moved in herds, almost certainly. The social organization of hadrosaurs is one of the most strongly supported behavioral inferences in dinosaur paleontology, supported by trackways, by nesting sites with evidence of communal use, and by the sheer abundance of their remains in many formations. They were vocal animals, with the complex cranial crests of some species, the Parasaurolophus, the Corythosaurus, the Lambeosaurus, serving as resonating chambers for producing distinctive calls. They were, in ecological terms, the great herbivore biomass of the late Cretaceous, the animal equivalent of the vast herds of ungulates that roam the African savanna today. And they were prey. Specifically, they were prey for the most iconic predator in the history of paleontology, Tyrannosaurus rex. The specimen at the center of this particular story is an Edmontosaurus, a large hadrosaur from the very end of the Cretaceous period, one of the last of the hadrosaurs, living in the same time and place as Tyrannosaurus rex and therefore existing in a predator-prey relationship with the largest terrestrial carnivore ever to evolve. An adult Edmontosaurus was not a small animal. It could reach 12 to 15 meters in length and weigh several tons. But a Tyrannosaurus rex was larger, heavier, and armed with jaws that delivered a bite force estimated at around 35,000 to 57,000 newtons, the most powerful bite of any terrestrial animal in the entire fossil record. The relationship between Edmontosaurus and Tyrannosaurus was one of the most unequal and brutal predator-prey dynamics in the history of life on land. And yet, sometimes prey escaped. Sometimes an Edmontosaurus survived an encounter with a Tyrannosaurus rex, and when it did, it left the encounter with evidence of that survival, evidence that could, under the right conditions of preservation, be read millions of years later by paleontologists with the right tools and the right questions. The specimen in question displays a remarkable, and initially baffling pathology. Embedded between two of the caudal vertebrae, the vertebrae of the tail, specifically in the proximal portion of the tail, not far from the base, is a foreign object. An object that the bone has grown around, incorporating it into the structure of the healed tissue in the way that living bone responds to persistent foreign objects embedded within it. The object is a tooth fragment. An isotopic analysis and morphological examination of that tooth fragment identified it as belonging to Tyrannosaurus rex. Let that sink in for a moment. A Tyrannosaurus rex bit this Edmontosaurus in the tail. The tooth, or a portion of a tooth, broke off and remained embedded in the flesh between the vertebrae. The Edmontosaurus escaped. And it lived long enough afterward, with that tooth fragment still in its tail, for the bone around it to begin growing and reshaping in response to the foreign object, a process that takes weeks to months at minimum and that represents unambiguous biological evidence of survival and ongoing life after the attack. The circumstances of the attack can be reconstructed with reasonable confidence from the anatomy and the position of the wound. A Tyrannosaurus attacking an Edmontosaurus would most likely have targeted the hindquarters, the flanks, the rump, the tail, areas that represent large, accessible masses of muscle and that a predator pursuing prey from behind or alongside would naturally target. An Edmontosaurus that was running, that was part of a herd, that had the collective movement of many animals around it. Such an animal might have managed to pull free from a bite that had not yet established a lethal grip. The tooth fragment left behind suggests a bite that was powerful enough to crack bone, powerful enough to drive a tooth into the space between vertebrae, but not powerful enough or not strategically placed enough to disable the prey animal before it could escape. The tooth of a Tyrannosaurus is not a delicate instrument. These teeth, the largest and most robust of any theropod, serrated like steak knives and set in jaws of extraordinary mechanical power, frequently sustained damage during feeding. Tooth breakage was common in Tyrannosaurus, and broken teeth and tooth fragments are found in association with hadrosaur remains in multiple sites from the Hell Creek Formation and equivalent deposits. The tooth that remained in this Edmontosaurus's tail was probably not noticed, in any experiential sense, by the Tyrannosaurus that lost it. For the Tyrannosaurus, it was simply another bite in the course of a hunt that was not successful. For the Edmontosaurus, it was the beginning of months of carrying a biological time bomb in its tail. A tooth fragment embedded between vertebrae is not a neutral foreign object. It is a source of chronic pain, of inflammatory response, and of potential infection. Every movement of the tail, and hadrosaurs used their tails extensively for balance and locomotion, would have pressed and shifted the embedded fragment against the surrounding tissue, stimulating a persistent inflammatory response and potentially causing recurring damage to the soft tissues around it. The bone growth around the fragment that we can observe in the fossil represents the body's attempt to wall off and stabilize the intrusion, but this process itself, the deposition of new bone around a foreign object, is not painless, and it would not have resolved the mechanical problem of having a pointed fragment of mineralized tissue wedged between two bones that needed to move relative to each other. How did this affect the Edmontosaurus's life? The tail is crucial for hadrosaur locomotion. It counterbalances the weight of the body, it assists in rapid movement, it is a key element of the biomechanical system that allows these animals to run. An injury in the proximal tail, between vertebrae, would have impaired the freedom of movement of the tail, potentially altering the animal's gait, reducing its maximum running speed, and affecting its ability to perform the rapid directional changes that are a prey animal's primary evasion strategy against predators. The bitter irony is almost too dramatic to contemplate. This Edmontosaurus escaped a Tyrannosaurus rex, an outcome that, on the statistical level, must have been relatively rare, given the power and hunting capability of the predator, only to be left with an injury that compromised the very abilities it needed most to survive in a world full of Tyrannosaurus rex. The escape that saved its life also left it slower, less agile, more vulnerable than it had been before, carrying inside it a permanent reminder of the encounter from which it had fled. And yet it lived. For weeks, for months, with the bone growing around the tooth fragment, it lived. It continued to move, to forage, to exist in the late Cretaceous landscape of the Hell Creek Formation, carrying its burden of pain and limitation. The fossil we have does not tell us how this particular story ended. We do not know the specific cause of death of this individual, whether it was eventually caught by a Tyrannosaurus or succumbed to infection, or died of some entirely unrelated cause. What we know is that it survived the initial attack long enough for significant bone healing to occur, and that in doing so, it demonstrated a resilience and a will to continue that is, in its own way, as remarkable as any of the other stories we have examined. The tooth fragment itself is perhaps the most haunting artifact in this entire account. A piece of the most iconic predator in paleontological history, preserved inside the vertebrae of its prey. Two animal stories locked together in a single piece of mineralized bone, separated by the moment of violence that connected them. The hadrosaur that ran, the tyrannosaurid whose tooth it carried, the months of living with that connection before the final end that all living things eventually reach. We turn now to one of the most famous dinosaur specimens in the history of vertebrate paleontology, an animal whose name has become almost shorthand for the concept of a dinosaur individual with a documented medical history. A specimen so extensively pathologized, so completely catalogued in its injuries and ailments, that researchers working on it had to develop new methodological frameworks simply to describe the sheer number and variety of things that had gone wrong with this animal's body over the course of its life. This is Big Al. The full official designation of this specimen is WDC-DML001, but the informal name Big Al, applied by the team that discovered and prepared the fossil, and subsequently adopted enthusiastically by the scientific community and the popular press, has become the name by which this extraordinary animal is universally known. Big Al is an Allosaurus fragilis, a large theropod predator of the late Jurassic period, discovered in the Morrison Formation of Wyoming, in rock dating to approximately 154 million years ago. In terms of geological age, Big Al is significantly older than the Cretaceous specimens we have been discussing, older than the Daspletosaurus, older than the Edmontosaurus, older even than the Titanosaur from Brazil. Big Al comes from an earlier chapter of the Age of Dinosaurs, from the world of the late Jurassic, when the dominant large predators were not the tyrannosaurids but their distant predecessors, the great allosaurs and their relatives. Allosaurus was the apex predator of its time. It was a large bipedal theropod, typically reaching 8 to 9 meters in length and weighing perhaps 2 to 3 metric tons, with a long, narrow skull armed with dozens of blade-like, recurved teeth, three-fingered hands tipped with large, curved claws, and the general body plan of a large, fast, and highly capable predator. Allosaurus has been found in large numbers in the Morrison Formation. It is one of the most commonly found large theropods in any fossil formation, and the abundance of its remains has allowed paleontologists to build a detailed picture of its anatomy, its growth patterns, its ecological role, and, in some cases, its individual life histories. Big Al was a subadult individual at the time of death, not yet fully grown, still in the rapid growth phase that characterizes juvenile and subadult theropods, but already a substantial predator, approximately 8 meters long and perhaps a ton or more in mass. The completeness of the skeleton is exceptional, approximately 95% complete, making it one of the most complete Allosaurus specimens ever found and allowing for an unusually thorough analysis of its anatomy and pathology. And the pathology is where Big Al becomes truly extraordinary. Researchers examining Big Al cataloged 19 separate pathological conditions across the skeleton. 19. In a single animal. This is not a random scatter of minor dings and bruises. This is a comprehensive medical biography of an animal that spent most of its life dealing with injury, infection, and physical damage. The pathologies include healed fractures in multiple elements, ribs, metatarsals, other skeletal components, that represent incidents of physical trauma that the animal survived and healed from, sometimes incompletely, leaving behind evidence of the bone remodeling that indicates survival without full restoration of normal function. There are osteomyelitic lesions, bone infections, in several elements, indicating that bacteria colonized damaged tissue and created chronic inflammatory foci that would have caused persistent pain and potentially impaired the function of the affected structures. There are avulsion injuries, damage caused by the forceful tearing of tendons or ligaments from their bony attachment points, typically associated with extreme muscular exertion or sudden violent trauma. But among all 19 of Big Al's pathologies, the one that has attracted the most scientific attention and that was almost certainly the most consequential for his survival is the infection in his right foot. Specifically in the bones of the right hind foot, the metatarsals and associated elements, there is evidence of severe, chronic osteomyelitis. This infection was not a recent development at the time of death. The bone changes associated with it indicate a long-standing, progressive condition that had been affecting this foot for a substantial period, possibly months or even longer. The foot is not an incidental body part for a large bipedal predator. It is fundamental to everything. An Allosaurus that cannot use its right hind foot effectively is an Allosaurus that cannot run at full speed, cannot pursue prey with the agility and power that successful hunting requires, cannot deliver the powerful, gripping kicks that theropod predators likely used in subduing large prey, and cannot move across the terrain of the Morrison Formation with the efficiency needed to find food and avoid larger threats. A compromised foot is a compromised hunter. And a compromised hunter, in an ecosystem where the prey animals are large, fast, and capable of defensive behavior, is an animal in serious nutritional trouble. The researchers who conducted the formal pathological analysis of Big Al, published in the scientific literature with the kind of detailed, methodical documentation that allows other scientists to evaluate and build on the findings, proposed that the foot infection was the primary driver of Big Al's decline and death. An Allosaurus unable to hunt effectively would rapidly lose body condition. The enormous caloric demands of maintaining a large, active predator's metabolism cannot be met without successful, frequent predation, and an animal that cannot hunt effectively begins to starve even in an environment full of potential prey. We can imagine, carefully, scientifically, with appropriate epistemic humility about the limits of inference across 154 million years, what Big Al's last weeks and months might have been like. An animal that is already carrying a host of chronic injuries and infections, whose right foot is increasingly compromised by a bone infection that has been growing for months, whose ability to run and to hunt is progressively reduced, foraging through the late Jurassic Morrison landscape in a state of increasing desperation. The Morrison Formation was not, it should be noted, a benign environment. It was a complex, seasonal ecosystem subject to prolonged droughts, and the large predators of the Jurassic faced competition not just from each other but from the difficulties of finding food during lean periods when the large herbivore herds were dispersed or scarce. Big Al was young, a subadult, an animal that had not yet reached the size and experience of a fully adult Allosaurus. The pathologies on his skeleton suggest that he had already had a hard life, that the normal activities of an Allosaurus in the Morrison Formation, hunting, competing with conspecifics and other predators, navigating a challenging physical environment, had already left significant marks on his body by the time the foot infection became critical. He was not an old animal worn down by decades of accumulated damage. He was a young animal whose luck had simply been consistently terrible, whose body had absorbed one injury after another without ever quite finding a period of extended recovery and recuperation. The foot infection was almost certainly the final chapter. Unable to hunt effectively, unable to cover ground efficiently, weakening from inadequate nutrition layered on top of the metabolic costs of fighting multiple ongoing infections and inflammatory conditions, Big Al died as a subadult in the late Jurassic landscape of what is now Wyoming. His body was buried in the sediments that would eventually become the Morrison Formation, and there it remained for approximately 154 million years, preserving in extraordinary detail the complete medical record of one individual life among the countless millions of individual lives that were lived and ended in the Mesozoic world. Big Al has become something of a cultural phenomenon beyond the purely scientific. He was the subject of a BBC documentary, a detailed artistic reconstruction, and extensive public interest in a way that very few individual paleontological specimens achieve. And the reason for that interest is clear. Big Al is not just a specimen. He is a story. He is a biography. He is the preserved record of a specific animal's specific life, with all of its difficulties and injuries and infections and struggles, written in bone that has survived longer than almost anything else that has ever existed on this planet. There is a particular kind of poignancy in the fact that Big Al was a predator. We tend, perhaps, to feel more automatic sympathy for prey animals, for the hadrosaur with a tyrannosaur tooth in its tail, for the titanosaur slowly weakened by parasites, for the oviraptorid parent buried alive on its nest. These are animals whose suffering is legible to us in a way that feels intuitive. But Big Al's story asks us to extend the same attention and the same acknowledgement of individual experience to the predator as well. He was not simply a hunting machine, a biological automaton designed to kill. He was an individual animal who suffered real injuries, real infections, real limitations, who tried to survive in a world that was difficult for everyone, predators and prey alike, and who ultimately failed to survive, not from any inherent weakness but from the accumulated bad luck of 19 separate pathological events that compounded each other until his body simply could not continue to function. 19 pathologies. Each one a moment of damage, of pain, of biological crisis that the animal's body responded to as best it could. Each one a chapter in a life story that ended too soon, that ended before Big Al reached the full size and power and experience of an adult Allosaurus. The stone that holds him preserves not a triumph but a tragedy, and in doing so, makes him one of the most humanly resonant objects in the entire fossil record. From the late Jurassic and the individual tragedy of Big Al, we step forward in time again, back into the late Cretaceous, back into the rich faunal communities of what is now Western North America, to encounter the final case study in the first part of our documentary. And this case, like the one that preceded it, involves an animal whose name is one of the most recognizable in the entire world of dinosaur paleontology, not quite as universally famous as Tyrannosaurus or Triceratops, but familiar to anyone who has spent time studying the extraordinary diversity of the Cretaceous world. Parasaurolophus is perhaps the most famous of all the Lambeosaurine hadrosaurs, the crested duck-billed dinosaurs whose elaborate hollow cranial structures have fascinated scientists and the public alike since their first discovery. The hollow crest of Parasaurolophus, curving dramatically backward from the skull like an elaborate curved tube, has been the subject of extensive scientific study and considerable speculation. The most widely accepted functional interpretation is that the crest served as a resonating chamber for producing distinctive, far-carrying vocalizations, a biological musical instrument, essentially, that allowed Parasaurolophus individuals to communicate across distance in ways that could be used for herd coordination, predator warning, mate attraction, and species recognition. CT scans of Parasaurolophus crests have revealed complex, interconnected nasal passages within the hollow structure, and computer modeling of these passages has produced sound reconstructions suggesting that the calls of Parasaurolophus would have been deep, resonant, and distinctive. Sounds quite unlike anything in the modern world. Sounds that once echoed across the Cretaceous landscapes of what is now the western interior, but that have been silent for 66 million years. The specific individual at the center of this final case in part 1 of our documentary is known scientifically as Parasaurolophus walkeri, the type specimen of the species, meaning the individual whose remains served as the basis for the formal scientific description and naming of the species. This specimen, the holotype of Parasaurolophus walkeri, was discovered in Alberta, in the Horseshoe Canyon Formation, in rock dating to approximately 73 to 75 million years ago. As the holotype of the species, it holds a special position in the taxonomy of the group. It is, in a real sense, the definitional Parasaurolophus walkeri, the individual against which all other specimens of the species are compared. And this definitional individual, this taxonomic reference point, this scientific cornerstone of one of the most studied and beloved of all hadrosaur species, had lived an extraordinarily difficult life, leaving behind in its bones a record of trauma so severe that researchers examining it were initially surprised that the animal had survived long enough to produce a fossil at all. The pathological analysis of the Parasaurolophus walkeri holotype has been carried out by multiple teams of researchers over the years, as analytical techniques have improved and as the value of applying detailed pathological methods to even well-known specimens has become more widely recognized. What those analyses have revealed is a catalogue of skeletal trauma that speaks of violence on a scale difficult to fully comprehend in the context of an animal that was, in most respects, a gentle and highly social herbivore. The specimen displays multiple healed fractures across a range of skeletal elements. These are not minor stress fractures or the kind of microdamage that accumulates with normal activity over time. These are major structural injuries, fractures in vertebrae, in ribs, in limb elements, that represent incidents of physical trauma significant enough to compromise the integrity of the skeleton itself. The healing around these fractures, while present, in some cases appears incomplete, suggesting that the animal was still in the process of recovering from one or more of these injuries at the time of its death, or that the healing had produced functional limitations rather than full restoration of normal biomechanical capability. What could have caused injuries of this magnitude in a hadrosaur? Parasaurolophus walkeri was an herbivore. It did not engage in the kind of active hunting and combat with large prey animals that might explain the accumulation of traumatic injuries seen in Big Al or the Daspletosaurus. It was not a combative animal in the way that the ceratopsians, with their horns and frills, sometimes were with each other. Its social behaviors appear to have been based more on vocalization and visual display than on physical combat. The hypothesis put forward by researchers to explain the severity and distribution of the traumatic injuries in this specimen involves a different kind of environmental violence entirely. The injury pattern, the specific locations and orientations of the fractures, the combination of spinal and rib involvement, is most consistent, in the judgment of the researchers who studied it, with blunt force trauma of a type that could be produced by a falling or crushing object. Specifically, the suggestion that has gained traction in the scientific literature is that this Parasaurolophus may have been struck by a falling tree. In the Cretaceous forests and floodplain environments that Parasaurolophus inhabited, large trees, cycads, conifers, angiosperms, were a constant feature of the landscape, and their occasional falling, whether from wind, flooding, rot, or the collateral damage caused by the movement of large animals through the vegetation, would have been a real hazard. A large tree striking an animal the size of a Parasaurolophus from above could produce exactly the pattern of vertebral, costal, and limb injuries that this specimen displays, a pattern of trauma concentrated along the dorsal and lateral aspects of the body in a way consistent with a crushing blow from above or to the side. This is not a glamorous way to be injured. There is nothing in this scenario of the dramatic predator-prey encounters or the fierce intraspecific combat of the ceratopsians. This is simply an accident. An animal in the wrong place at the wrong moment, struck by the ordinary physics of a large tree falling in a forest. An accident that should, by any reasonable assessment of the injuries involved, have been fatal. Multiple fractured vertebrae and ribs represent a level of trauma that, in the context of modern veterinary medicine, would often be considered unsurvivable, or at the very least incapacitating to the point where an animal in the wild would rapidly succumb to secondary effects, inability to move to food and water, vulnerability to predation, shock and systemic response to massive trauma. And yet this Parasaurolophus did not die immediately. The bone healing that is evident around these injuries, the periosteo response, the callus formation, the beginning of remodeling, is unambiguous evidence that this animal survived the initial trauma and continued to live for a period afterward. The estimates of survival time based on the degree of bone healing are, again, in the range of weeks to months, not days, not simply the immediate aftermath of the injury, but a substantial period of continued life during which the animal's body was actively working to repair the damage. How did it survive? How did an animal with multiple fractured vertebrae and ribs continue to exist in an environment where predators, including Albertosaurus and other large theropods, were real and constant threats, where the need to move to find adequate food was not optional, and where the kind of care and protection that might allow a severely injured human being to survive through a lengthy recovery period simply did not exist? The answer, as with so many of the cases we have examined, is that the biological resilience of these animals was extraordinary by any standard. The healing mechanisms built into the vertebrate skeleton are powerful, and the drive to survive, whatever neurological and hormonal substrates underlie that drive in non-avian dinosaurs, appears to have been powerful enough in this individual to sustain life through an experience of trauma that defies easy comprehension. The Parasaurolophus walkeri holotype is the definitional specimen of its species, the individual from which the species was described and named. And what the pathological analysis of this individual reveals is that the archetypal Parasaurolophus walkeri was an animal in pain. An animal carrying the evidence of a near-fatal accident, surviving through weeks or months of recovery, living out its remaining time in the late Cretaceous landscape of Alberta with a body that was compromised and battered but still, somehow, functional. Still breathing. Still moving through the world. Still sounding, perhaps, those deep and resonant calls through the hollow chambers of its crest, communicating with the herd in a voice that the ancient forests of the Cretaceous would never hear again after the mass extinction that was approaching, inexorably, from space. The holotype of Parasaurolophus walkeri reminds us that even in the most apparently ordinary of lives, the life of a social herbivore, moving through familiar landscapes in the company of its own kind, the Mesozoic world held dangers that were not always predatory, not always dramatic, not always the stuff of cinematic encounters between giant predators and desperate prey. Sometimes danger was simply a tree, falling at the wrong moment. Sometimes survival was simply a matter of stubborn biological persistence, of a body that refused to stop repairing itself, of a metabolism that continued to function even under the load of massive trauma, of an animal that kept moving forward through the pain because moving forward is what living things do. As we come to the end of the first part of this documentary, it is worth stepping back and considering what the cases we have examined: Big John the Triceratops with his infected horn wound, the Brazilian Titanosaur with its blood parasites and osteomyelitis, the Daspletosaurus that fought its own kind and was scavenged after death, the oviraptorid parent buried alive on its nest, the Edmontosaurus carrying a Tyrannosaurus tooth in its tail, Big Al with his 19 pathologies and his fatal foot infection, and the battered holotype of Parasaurolophus walkeri. What these cases, taken together, tell us about the world of the Mesozoic. They tell us that it was a world of extraordinary difficulty. Not just the dramatic difficulty of predator-prey relationships, though that was certainly real and terrifying, but the grinding, unglamorous, daily difficulty of maintaining a living body in an environment full of disease vectors, parasites, accidents, intraspecific aggression, and the ever-present possibility of injury from any of 100 different sources. They tell us that the dinosaurs were not simply biological machines, perfectly adapted to their environments and functioning smoothly until the moment of their death. They were living things in the fullest sense of that phrase, struggling, suffering, healing, declining, surviving against the odds in some cases and succumbing in others, always being acted upon by the forces of a world that was indifferent to their individual survival. They tell us that modern paleontology has reached a point where the fossils of these ancient animals can be read not just as specimens, not just as data points in the taxonomic and phylogenetic analysis of ancient biodiversity, but as individual stories, as biographical documents, as the preserved medical histories of real creatures with real lives, and that reading those histories carefully, with the right tools and the right questions, reveals a world that is simultaneously more brutal and more familiar than the popular conception of the age of dinosaurs has typically acknowledged. And perhaps most importantly, they remind us that the bones that we pull from the ground and place in museums and study in laboratories are not simply objects. They are the remains of living things. They are the last physical connection between the present world and lives that were lived tens or hundreds of millions of years ago, in conditions so different from our own that the landscape, the atmosphere, the plant communities, the sound of the wind, everything would be utterly alien to us. And yet, in the suffering recorded in these bones, in the healing, in the persistence, in the stubborn continuation of life in the face of injury and disease, something remains that is not alien at all. Something remains that is deeply, fundamentally, inescapably alive. Welcome back. If you have been with us from the beginning, you have already witnessed something extraordinary. You have seen the evidence, written in ancient bone, preserved across tens of millions of years, decoded by some of the most meticulous scientists working in any discipline today, of individual dinosaur lives defined by suffering, resilience, and ultimately by the inescapable reality of death. You have met Big John, the Triceratops who survived a horn strike through his frill only to be consumed by infection from within. You have encountered a Brazilian Titanosaur whose blood was colonized by parasites so small they could never be seen, yet powerful enough to bring down one of the largest animals ever to walk the earth. You have stood in the presence of a Daspletosaurus that fought its own kind, bore the healed scars of that violence on its skull, and was ultimately consumed after death by another predator, possibly another member of its own species. You have witnessed the heartbreaking preservation of an oviraptorid parent, buried alive in the act of protecting its unhatched offspring. You have traced the journey of an Edmontosaurus that escaped the jaws of a Tyrannosaurus rex but carried a fragment of its attacker's tooth embedded in its spine for months afterward. You have catalogued the 19 pathologies of Big Al, the young Allosaurus whose chronic foot infection slowly starved him in a world where the ability to run was the difference between eating and dying. And you have stood beside the battered holotype of Parasaurolophus walkeri, an animal that survived what was almost certainly a catastrophic impact from a falling tree and lived on through weeks or months of recovery with a body that was broken in ways that should have been terminal. These are not hypothetical scenarios. These are not the inventions of dramatists, or the speculations of enthusiasts. They are forensic reconstructions based on physical evidence that has survived across geological time, evidence that is as real and as readable as the medical records that a modern hospital generates for every patient who passes through its doors. The difference, of course, is one of scale, not days or weeks or years, but tens of millions of years, bridged by the extraordinary durability of mineralized bone and the equally extraordinary ingenuity of the scientists who have learned to read it. In this second part of our documentary, we are going to go deeper. We are going to revisit each of these cases with additional detail, examine the scientific methodologies that made these discoveries possible, explore the broader ecological and evolutionary implications of what the pathological evidence reveals, and weave together a comprehensive picture of a world, the Mesozoic world, the world of the dinosaurs, that was far more complex, far more dangerous, and far more medically interesting than anyone could have imagined even a few decades ago. Let us begin by returning to Big John, because there is more to say about this extraordinary Triceratops than we were able to cover in Part 1, and because the scientific analysis of his wound tells us things about ceratopsian biology that extend far beyond the story of a single individual. When the research team from the University of Bologna and their collaborators published their formal analysis of the wound in Big John's frill, they did not simply describe the macroscopic appearance of the injury, the shape of the hole, the evidence of healing around its margins. They went further, applying techniques borrowed from materials science and biomedical engineering to examine the bone at a level of detail that would have been impossible for earlier generations of paleontologists. They used scanning electron microscopy, a technique that produces images at magnifications far beyond the capability of optical microscopes, to examine the surface texture and microstructure of the bone surrounding the wound. They used energy-dispersive X-ray spectroscopy to analyze the chemical composition of the bone tissue at different points around the injury, looking for the chemical signatures of biological processes associated with healing and infection. And they conducted histological analysis, the preparation and examination of thin sections of bone under microscope, to examine the internal structure of the tissue at the cellular level. What these analyses revealed was a picture of extraordinary biological complexity. The bone around the wound margin was not simply healing in the straightforward, linear fashion that a healthy bone repair process would produce. Instead, the tissue showed evidence of what the researchers described as a disorganized healing response, new bone being laid down in irregular patterns, with areas of abnormally dense tissue adjacent to areas of abnormally porous tissue, the whole pattern suggesting that the healing process was being disrupted by ongoing infection and inflammation. The researchers identified specific features of the bone microstructure that are diagnostic of osteomyelitis, including the presence of what are called involucra, layers of new bone formed by the periosteum around infected tissue in an attempt to wall off and contain the infection, and cloacae, channels or openings in the bone's surface through which pus and infected material drain from the interior of the bone to the outside. These are features that are well recognized in modern clinical medicine as hallmarks of bone infection, and their presence in Big John's frill provided definitive confirmation that the wound was not simply healing poorly but was actively infected with bacteria. The distribution of the infection across the frill is itself informative. The infected zone is not confined to the immediate area of the wound but extends outward from it in a pattern that suggests the infection was spreading through the bone at the time of the animal's death. This spreading pattern is consistent with the progression of untreated osteomyelitis in modern animals, where infection typically begins at a point of entry, in this case, the puncture wound, and then propagates through the bone via the vascular channels and marrow spaces, gradually expanding the zone of infected and damaged tissue. The chemical analysis of the bone adds another dimension to this picture. The researchers found that the bone tissue around the wound showed elevated levels of certain trace elements, including iron and sulfur, that are associated with the presence of blood breakdown products and bacterial metabolic waste. These chemical signatures are consistent with a wound environment in which there was active bleeding, active infection, and active inflammatory response. In other words, a wound that was not healing cleanly but was instead a site of ongoing biological conflict between the animal's immune system and the invading microorganisms. All of this evidence, taken together, paints a picture of an animal in the final stages of a losing battle against infection. Big John's immune system was fighting. His body was generating new bone, trying to wall off the infection, trying to contain the bacterial invasion. But the infection was winning. It was spreading through the frill bone, it was producing the kind of tissue destruction that is associated with progressive, uncontrolled osteomyelitis, and the chemical evidence suggests that it was generating systemic effects, products of infection and inflammation that would have been carried through the bloodstream to the rest of the body, affecting organ function, metabolic regulation, and the overall physiological stability of the animal. The cause of death was almost certainly sepsis, a systemic infection in which bacteria and their toxic products overwhelmed the body's ability to maintain normal physiological function. Sepsis in modern animals is characterized by fever, rapid heart rate, altered mental status, organ dysfunction, and eventually cardiovascular collapse. We cannot know the exact clinical progression of Big John's final hours or days, but the pathological evidence is consistent with an animal that was becoming progressively sicker, that was losing the battle against infection on a systemic level, and that ultimately died when the cumulative burden of infection exceeded the body's capacity to compensate. The duration of survival that the bone remodeling evidence suggests, approximately 6 months, tells us something important about the resilience of Triceratops biology. 6 months is a long time to survive with an actively infected penetrating wound in a bony structure as richly vascularized as the frill. It suggests that the immune system of Triceratops was robust, that the animal's overall health was otherwise good, and that the physiological resources available to combat infection were substantial. This animal did not die quickly or easily. It fought, biologically speaking, for half a year before the infection finally overwhelmed its defenses. There is a broader context to the story of Big John's wound that deserves attention as well. The wound in the frill, inflicted by the horn of another Triceratops, is not an isolated observation. Across the ceratopsian fossil record, a significant proportion of frill bones, particularly in the large chasmosaurine ceratopsians like Triceratops, Torosaurus, and their relatives, display lesions, perforations, and other damage consistent with intraspecific combat. A 2009 study by Andrew Fark and colleagues examined a large sample of ceratopsian frills and found that the rate of lesions on the squamosal bones, the bones that make up the lateral portions of the frill, was significantly higher in Triceratops than in the related genus Centrosaurus, and that the pattern of lesion distribution was consistent with combat between individuals using their horns as weapons. This comparative evidence strengthens the interpretation of Big John's wound as the result of intraspecific combat, and places it within a broader behavioral pattern that appears to have been a significant component of ceratopsian social ecology. These animals fought each other, regularly, with enough force to inflict serious injuries. The evolutionary drivers of this behavior, competition for mates, territory, social status, are the same drivers that produce intraspecific combat in modern animals, from deer to elephants to marine iguanas. The difference is one of scale and armament, a Triceratops weighing perhaps 10 tons, equipped with horns that could reach over a meter in length, fighting another animal of similar size and armament, would have produced collisions and impacts of extraordinary violence, impacts that the frill was partially designed to withstand but that could, under the right circumstances, overcome even that formidable defense. Big John was caught by such an impact. His frill failed to protect him. The horn of his attacker penetrated it cleanly, breaching the defensive barrier and creating a wound that the animal's immune system could not ultimately contain. He survived the initial violence, but not the insidious aftermath. And in his survival and his eventual defeat, he provides us with one of the most detailed case studies of infection-mediated mortality in the entire Mesozoic fossil record. The Brazilian Titanosaur and its hemoparasites deserve further exploration as well, because the implications of this discovery ripple outward into questions about Mesozoic ecology that are far bigger than any single specimen. To appreciate why the discovery of blood parasites in a Cretaceous dinosaur is so significant, we need to understand how rare and how difficult it is to find direct evidence of parasitism in the fossil record. Parasites, by their very nature, tend to be soft-bodied organisms. They do not have the hard shells, the mineralized skeletons, the durable teeth and claws that give larger organisms their best chance of preservation as fossils. The vast majority of the parasitological diversity that has existed throughout the history of life on Earth has left no direct trace in the fossil record whatsoever. We know that parasites must have existed in the Mesozoic because they exist in every modern ecosystem, because the phylogenetic relationships of modern parasite groups imply ancient evolutionary origins, and because occasional spectacular finds, parasites preserved in amber, parasite eggs preserved in coprolites, confirm that parasitism was a feature of ancient ecosystems. But direct evidence of parasites affecting the bones of their dinosaur hosts, leaving pathological signatures that can be identified and interpreted millions of years later, is extraordinarily rare. The Brazilian Titanosaur specimen represents, therefore, a discovery of immense importance not just for understanding the life and death of one individual animal, but for understanding the hidden biological architecture of Mesozoic ecosystems as a whole. The hemoparasites that infected this titanosaur, identified through their effects on the vascular channels of the bone, their disruption of normal vascular anatomy, and the inflammatory and osteomyelitic responses they triggered, represent the tip of an enormous unseen iceberg. If these parasites were present in one titanosaur from late Cretaceous Brazil, they were almost certainly present in many others. And if hemoparasites were a significant ecological factor in the lives of sauropod dinosaurs, then the same was almost certainly true of other dinosaur groups, other Mesozoic vertebrates, and the broader community of organisms that inhabited these ancient ecosystems. The researchers who studied this specimen employed a battery of analytical techniques to confirm the parasitic nature of the bone pathology. They conducted thin-section histological analysis, cutting extremely thin slices of the affected bone and examining them under microscope with various lighting techniques. Polarized light, which reveals details of mineral crystallography and tissue organization that are invisible under ordinary illumination, and transmitted light, which allows the internal structures of bone tissue to be examined in detail. They compared the pathological features they observed against an extensive database of known pathologies in modern reptilian bone, drawing on veterinary literature and comparative anatomy to establish the diagnostic criteria for parasitic bone disease as opposed to other causes of osteomyelitis. The hemoparasites themselves, the actual organisms that infected the titanosaur's blood, are not preserved as intact organisms. They are preserved only indirectly, through their effects on the host's tissues. This is analogous to the way that a modern physician might diagnose a parasitic infection not by seeing the parasite directly but by observing the characteristic tissue changes that the parasite produces, the inflammatory infiltrates, the granulomas, the specific patterns of tissue destruction that are diagnostic of particular types of parasitic disease. In the case of the Brazilian Titanosaur, the researchers identified features in the vascular channels of the bone that are consistent with the presence of Hemosporidian parasites, a group that includes the organisms responsible for avian malaria in modern birds. The connection to avian malaria is particularly significant because birds are the living descendants of theropod dinosaurs. They are, in a real evolutionary sense, dinosaurs themselves, the one lineage of the great dinosaurian radiation that survived the end Cretaceous mass extinction and continues to the present day. The Hemosporidian parasites that cause malaria in modern birds are known to have deep evolutionary roots, and their phylogenetic relationships suggest that they have been parasitizing avian and pre-avian hosts for tens of millions of years or longer. The discovery of evidence for Hemosporidian-like parasites in a Cretaceous dinosaur, even one from a non-theropod lineage like the Titanosaurs, is consistent with the hypothesis that these parasites were widespread across Mesozoic dinosaur communities and that their evolutionary history is deeply intertwined with the evolutionary history of their dinosaurian hosts. The vector question is also worth exploring. Hemosporidian parasites in modern birds are transmitted by blood-feeding insects, mosquitoes, biting midges, and other dipterans that take blood meals from their vertebrate hosts and, in the process, introduce parasitic organisms from one host to another. The fossil record of blood-feeding insects in the Mesozoic is substantial. Mosquitoes of modern aspect are known from Cretaceous amber deposits. The famous amber-preserved mosquitoes that inspired certain works of fiction are based on real fossil specimens. Biting midges, black flies, and other blood-feeding insects are also known from Mesozoic deposits. The biological infrastructure for the transmission of blood parasites between dinosaur hosts was unquestionably present in the Cretaceous world, and the Brazilian Titanosaur provides the most direct evidence yet discovered that this transmission was actually occurring and that it was producing clinically significant disease in the dinosaur hosts. The pathological progression from hemoparasitic infection to osteomyelitis to immobility and death represents a cascade of biological failure that deserves detailed examination. In modern animals with severe hemoparasitic infections, the parasites colonize red blood cells, causing their destruction, a process called hemolysis. Severe hemolysis leads to anemia, which reduces the oxygen-carrying capacity of the blood and places all organ systems under metabolic stress. The immune response to the infection generates widespread inflammation, which can damage blood vessels and compromise the blood-brain barrier, leading to neurological symptoms. The metabolic waste products of the parasites and the breakdown products of destroyed red blood cells must be processed and eliminated by the liver and kidneys, placing additional stress on those organ systems. And the systemic immune suppression that accompanies severe parasitic infection opens the door to secondary bacterial infections, which is precisely what appears to have happened in the case of the Brazilian Titanosaur, where bacteria colonized the bone tissue and established the osteomyelitic infection that ultimately compromised the animal's mobility and led to its death. For a titanosaur, an animal with a metabolic rate that, while lower than that of a mammal of equivalent size, was still enormous in absolute terms, the combination of anemia, systemic inflammation, organ stress, and secondary bone infection would have been catastrophic. These animals needed to consume vast quantities of vegetation every day to fuel their bodies, and they needed to be able to move across the landscape to find that vegetation. Even a modest impairment in the efficiency of oxygen delivery to the tissues, the kind of impairment that severe anemia produces, would have reduced the animal's exercise capacity, its ability to sustain prolonged movement, and its overall physiological performance. Add to that the pain and structural compromise of osteomyelitis in the weight-bearing bones, and the picture that emerges is one of progressive, accelerating decline. There is a lesson in the story of this titanosaur that extends beyond the specifics of dinosaur paleontology, and into the broader realm of ecology and evolutionary biology. The lesson is that size is not safety. The titanosaurs represent the most extreme expression of the evolutionary strategy of gigantism, the idea that being bigger makes you safer, harder to predate, more capable of dominating your environment through sheer mass. And in many respects, that strategy was enormously successful. Titanosaurs thrived for tens of millions of years across multiple continents, and their gigantic size almost certainly rendered adult individuals immune from predation by all but the largest predators. But size provides no defense against the microscopic world. A parasite small enough to inhabit a red blood cell does not care how large its host is. A bacterium colonizing bone tissue is not deterred by the fact that the bone belongs to an animal weighing 50 tons. The weapons of the microscopic world, infection, parasitism, immune disruption, operate on a scale where the advantages of gigantism are meaningless, and even the most massive animal ever to walk the earth can be brought low by organisms it cannot see, cannot feel, and cannot fight. The Daspletosaurus of Alberta, with its heel-bite wounds and its post-mortem scavenging, opens up a window into a behavioral world that paleontology has only begun to explore in the kind of detail that these specimens demand. Let us look more carefully at what the bite marks tell us about the social behavior of large tyrannosaurids, because this is a question that has generated enormous scientific debate and that the evidence from pathological specimens is beginning to resolve. The question of whether tyrannosaurids were social animals, whether they lived in groups, hunted cooperatively, or maintained any form of organized social structure, has been debated since the discovery of multiple tyrannosaurid individuals in close association at certain fossil sites. The most famous of these sites is a bone bed in Alberta that produced multiple Albertosaurus individuals of various sizes and ages, interpreted by some researchers as evidence of a social group that was killed and buried together. Similar associations have been found for Daspletosaurus and, more controversially, for Tyrannosaurus rex itself. But the interpretation of these associations is not straightforward. Animals do not need to be social to be found together in death. A drought-induced waterhole, a natural trap, or simple coincidence of burial could concentrate the remains of multiple individuals without those individuals having been part of a social group in life. The pathological evidence from the Daspletosaurus skull provides a different, and in some ways more compelling line of evidence about intraspecific behavior. Heel-bite wounds on the face and skull tell us that this animal was bitten by another large tyrannosaurid and survived the encounter. The pattern of the wounds, their location on the facial region, their morphology, their consistency with the dentition of a similarly sized tyrannosaurid, is consistent with a specific type of social interaction, face biting, a behavior that has been documented in multiple tyrannosaurid specimens and that appears to have been a characteristic feature of tyrannosaurid social ecology. Face biting in modern animals is typically associated with dominance interactions, contests for social rank, territory, or access to mates that involve direct physical confrontation but that are structured and ritualized to some degree, stopping short of the all-out lethal combat that would serve either participants' evolutionary interests. In crocodilians, for example, face biting and jaw locking are common components of territorial and mating disputes between males, and these interactions frequently result in healed wounds that are visible on the skulls of adult individuals. The parallel with tyrannosaurid face biting is striking and has been noted by multiple researchers. If tyrannosaurid face biting represents a form of intraspecific dominance interaction, then its prevalence in the fossil record, healed bite marks on the skulls and facial bones of tyrannosaurids have been reported from multiple specimens across multiple species, suggests that these interactions were a regular and important component of tyrannosaurid social life. This does not necessarily mean that tyrannosaurids were social in the way that wolves or lions are social. It is possible that face biting occurred primarily or exclusively between otherwise solitary individuals competing for territory or mates, and that the day-to-day existence of these animals was largely solitary. But it does mean that tyrannosaurids were not simply mindless killing machines operating in ecological isolation from their own kind. They had social interactions. Those interactions involved physical contact. And sometimes that physical contact was violent enough to leave permanent marks on bone. The post-mortem scavenging of the Daspletosaurus specimen adds another layer to this picture. The evidence that another large tyrannosaurid, quite possibly another Daspletosaurus, fed on the carcass after death raises questions about the role of cannibalism and scavenging in tyrannosaurid ecology. In modern ecosystems, cannibalism is most common in situations of nutritional stress, but it also occurs in some species as a normal component of behavior. Komodo dragons, for example, will readily consume dead members of their own species. If Daspletosaurus practiced opportunistic cannibalism, consuming the remains of dead conspecifics when the opportunity arose, this would represent a biologically rational strategy for maximizing caloric intake in an environment where large prey captures were energetically expensive and not always successful. The scenario that emerges from the combined evidence of the healed bite wounds and the post-mortem feeding marks is one of a complex social and ecological world for late Cretaceous tyrannosaurids, a world in which individuals encountered each other, competed physically, sometimes inflicted serious injuries, and sometimes consumed each other's remains after death. It is a world that is far more nuanced and far more biologically interesting than the simple predator-prey narratives that have traditionally dominated popular understanding of these animals. And it is a world that we are only beginning to see clearly through the lens of pathological fossil analysis. The specific Daspletosaurus individual whose bones tell this story lived in that world for what was probably a substantial portion of a natural tyrannosaurid lifespan. The healing of the facial bite wounds indicates a survival period of weeks to months after the intraspecific encounter, and the overall preservation of the specimen suggests an animal that was not a juvenile but a mature or near-mature individual that had accumulated the physical evidence of a life lived in the full intensity of the late Cretaceous predator ecology. This was an animal that had hunted, that had competed, that had fought and been wounded and healed and continued to hunt and compete until whatever final cause of death overtook it and left its body available for the scavenger that left the second set of marks on its bones. The oviraptorid parent from the Gobi Desert deserves further examination not only for what it tells us about the individual animal that was preserved but for what it tells us about the deep evolutionary history of parental behavior in the dinosaur-to-bird lineage. The brooding posture preserved in this specimen, the body positioned over the nest, the arms spread outward and downward in a wing-covering position, is not unique to this individual. Multiple oviraptorid specimens have been found in similar brooding postures over nests of eggs, from localities across the Gobi Desert and from equivalent age deposits in what is now northern China. The consistency of the posture across multiple independent specimens, each preserved by separate catastrophic burial events, provides very strong evidence that this was a genuine, species-typical behavior and not an artifact of a single unusual circumstance. The implications of this behavior for our understanding of the evolution of parental care are profound. Birds, the living descendants of theropod dinosaurs, are famous for the complexity and diversity of their parental care behaviors. From the simple ground nesting of some shorebirds to the elaborate nest building and cooperative breeding of corvids and certain raptors, avian parental care represents one of the most successful behavioral adaptations in the history of vertebrate evolution. The discovery that the non-avian theropod ancestors of birds were already engaging in brooding behavior, sitting on nests, using feathered arms to cover and thermoregulate eggs, maintaining physical contact with clutches during the incubation period, demonstrates that this behavioral complex did not originate with the evolution of flight or with the radiation of modern bird lineages, but was instead a much more ancient feature of the theropod lineage, one that was already well established by the late Cretaceous in animals that could not fly and that bore only a superficial resemblance to the birds we know today. The specific posture of the oviraptorid from Jangi provides additional information about the mechanics of non-avian theropod brooding. The arms are extended outward from the body in a manner that creates a wide spread, a posture that, in an animal with substantial arm feathers, would have created a broad covering surface capable of shielding a large area of nest. The legs are folded beneath the body in a posture that lowers the center of mass and brings the torso into close contact with the upper surfaces of the eggs. The tail appears to have been positioned around the perimeter of the nest in some specimens, creating a continuous barrier of body and feather around the clutch. This posture is strikingly similar to the brooding posture of modern ground-nesting birds like ostriches and emus, which use their wing feathers to cover and shade their nests during incubation, and the comparison suggests a direct behavioral homology between non-avian oviraptorid brooding and the brooding behavior of modern ratite birds. The eggs themselves provide additional evidence of reproductive biology. In specimens where the eggs have been preserved well enough for internal examination, researchers have found embryonic remains inside some of the eggs, confirming that these were indeed the parent's own eggs and that the eggs were at various stages of development at the time of burial. The arrangement of the eggs in a ring pattern, with the adult positioned at the center, is characteristic of oviraptorid nesting sites and suggests a specific sequence of egg-laying and nest arrangement that the parent followed as part of its reproductive behavior. One of the most intriguing aspects of oviraptorid nesting biology is the question of which parent was doing the brooding. In modern birds, both biparental care, where both parents share incubation duties, and uniparental care, where one parent does all or most of the incubation, are common, with the specific pattern varying widely across species. In some ground-nesting birds, particularly certain shorebirds and ratites, it is the male parent that does most or all of the incubation, a pattern that has been cited as potentially informative about the ancestral condition in the dinosaur-to-bird transition. Some researchers have argued, based on the size relationship between the brooding adult and the clutch in oviraptorid specimens, that the brooding parent in oviraptorids was most likely the male, a hypothesis that, if correct, would push the origin of male-dominated incubation behavior back into the non-avian dinosaur lineage, and would suggest that the behavioral repertoire of these animals was even more complex than the brooding posture alone suggests. The death of this particular individual, smothered under rapidly accumulating sand while maintaining its brooding position, speaks to the intensity of the parental drive that governed its behavior. Whatever stimulus the approaching sandstorm or collapsing dune provided, the visual cue of approaching sand, the tactile sensation of particles striking the body, the auditory signal of the wind, did not override the imperative to remain on the nest. The animal held its position. It held its posture. And it died in the configuration that evolution had designed it to maintain during the most critical phase of its reproductive cycle. Whether we choose to describe this as instinct, as dedication, as love, or simply as neurological programming is, to some extent, a question of philosophical preference rather than scientific determination. What is not a matter of preference is the biological reality that this animal's brain, shaped by millions of years of natural selection, contained circuits that prioritized nest protection over self-preservation in the face of immediate environmental threat, and that those circuits were powerful enough to hold the animal in place even as the sand buried it alive. That is a remarkable biological reality, however we choose to describe it in human terms. The preservation of this moment, this snapshot of behavior frozen in geological time, is one of the great gifts of the fossil record. It gives us something that bones alone can never provide, a window into what an animal was doing, not just what it looked like. And what this animal was doing, in the final moments of its life, was protecting its young. Across 70 million years, that image endures. Let us return now to the Edmontosaurus and its embedded tyrannosaur tooth, because there are aspects of this case that illuminate fundamental questions about predator-prey dynamics in the late Cretaceous that we did not fully explore in Part 1. The first question that arises from this specimen is a quantitative one. How often did hadrosaurs survive attacks by Tyrannosaurus rex? The traditional view of Tyrannosaurus as an invincible superpredator, a killing machine so powerful that any encounter between it and a prey animal was necessarily fatal for the prey, is not supported by the evidence. While Tyrannosaurus was unquestionably formidable, the reality of predation in any ecosystem is that not every hunt is successful. Modern large predators, lions, wolves, tigers, great white sharks, fail to make a kill in the majority of their hunting attempts. The success rate varies by species and by circumstance, but failure rates of 50 to 90% are typical for large predators hunting large prey. There is no reason to assume that Tyrannosaurus was significantly more efficient than modern predators, and considerable reason to think that its hunting success rate may have been comparable. And Edmontosaurus was not a helpless victim. It was a large, powerful animal, 12 to 15 meters long, weighing several tons, with strong limbs adapted for rapid locomotion and a social structure that likely included herd behavior with associated predator detection and avoidance strategies. An Edmontosaurus that detected an approaching Tyrannosaurus at sufficient distance could potentially outrun it, particularly if the Tyrannosaurus was large and heavy and therefore limited in its acceleration and sustained speed. The biomechanics of Tyrannosaurus locomotion have been studied extensively, and while the details remain debated, many researchers believe that the largest adult Tyrannosaurus individuals were not capable of the sustained high-speed pursuit running that is necessary for a chase predator. They were more likely ambush predators, relying on short bursts of speed to close the distance to prey before the prey could react and flee. In this context, the survival of the Edmontosaurus becomes less surprising and more expected. A Tyrannosaurus lunging at a fleeing hadrosaur from close range manages to land a bite on the tail, the trailing edge of the prey, the last part of the body to pass through the predator's strike zone. The bite is powerful enough to drive a tooth into the tissue between the vertebrae, but the hadrosaur's momentum carries it forward and out of the jaws before the bite can be consolidated. The tooth, or part of it, breaks off and remains embedded in the prey's tail as the hadrosaur escapes. The Tyrannosaurus is left with a mouthful of nothing and a gap in its dentition, a gap that will fill in over the following weeks as a replacement tooth grows in, because tyrannosaurids, like all theropod dinosaurs, replace their teeth continuously throughout life in a process analogous to the tooth replacement seen in modern crocodilians and sharks. The Edmontosaurus, meanwhile, is running with a fragment of tyrannosaur tooth embedded between its caudal vertebrae. The immediate effects of the bite would have been severe: pain, tissue damage, local hemorrhage, the shock of a violent physical encounter with the most dangerous predator in its environment. But the long-term effects, which are what the fossil record preserves, are what make this case so fascinating. The bone growth around the embedded tooth fragment is a process called reactive osteogenesis, the formation of new bone in response to a persistent irritant or foreign object. In modern clinical medicine, reactive osteogenesis around embedded foreign objects is well documented and well studied. The body's response to a foreign object that it cannot expel is to encapsulate it, to surround it with fibrous tissue and, eventually, with bone, creating a barrier between the foreign material and the living tissue of the host. This process is not painless. The formation of new bone around a foreign object in a mechanically active part of the skeleton, like the tail of a hadrosaur, which is in constant motion during locomotion, would have been associated with persistent inflammation, chronic low-grade pain, and the biomechanical effects of having additional, irregular bone mass in an area that was designed to move freely. The position of the tooth fragment, between the caudal vertebrae and the proximal tail, is significant because this region of the tail is crucial for the insertion of the caudal musculature that powers hindlimb locomotion. In hadrosaurs, as in most bipedal and quadrupedal dinosaurs, the muscles that drive the hind limbs originate in part from the caudal vertebrae, and the tail serves as a muscular anchor and counterbalance for the entire posterior body. Any disruption to the biomechanics of this region, any pain, any stiffness, any irregular bone growth that impedes the free movement of adjacent vertebrae, would have had direct effects on the animal's ability to move efficiently and at speed. We do not know how this Edmontosaurus ultimately died. The cause of death is not preserved in the fossil record for this individual. It may have been caught by another Tyrannosaurus, its compromised tail reducing its ability to flee effectively. It may have died of infection related to the embedded tooth. It may have died of entirely unrelated causes: disease, drowning, old age. What we know is that it survived the initial encounter, that it lived for a substantial period afterward, and that the embedded tooth fragment served as a constant, inescapable physical reminder of the moment when it came within a single bite of being killed by the most powerful terrestrial predator that has ever existed. The tooth itself, that small, broken fragment of tyrannosaur dentition, now encased in the bone of its former prey, is one of the most evocative objects in all of paleontology. It is a point of connection between predator and prey, frozen in stone. Two animals, one an apex predator and the other a massive herbivore, linked by a moment of violence that each survived, one by escaping, the other by losing a tooth. The predator went on to hunt again, grew a replacement tooth, and lived the rest of its life never knowing or caring that a piece of itself was being carried through the Cretaceous landscape in the tail of a hadrosaur it had failed to kill. The prey went on to live with the evidence of that encounter lodged permanently in its spine, a constant source of pain and limitation, a daily physical reminder that in the world of the late Cretaceous, survival was never guaranteed and safety was never permanent. Big Al's 19 pathologies warrant a more detailed examination than we were able to provide in Part 1, because the sheer breadth and diversity of his injuries illuminate the full range of physical challenges that a Mesozoic predator could face, and because the interaction between his multiple conditions provides a case study in the cumulative effects of chronic illness and injury on a large theropod. Let us catalog the pathologies more carefully. In addition to the chronic osteomyelitis of the right foot that we discussed at length in Part 1, Big AL's skeleton displays the following conditions, each of which tells its own story about a specific incident or process in the animal's life. Rib fractures. Multiple ribs show evidence of healed fractures, areas where the bone has been broken and then repaired, with visible callus formation marking the sites of the original breaks. Rib fractures in large theropods can result from a variety of causes: impacts with prey animals during hunting, falls during rapid locomotion over uneven terrain, interactions with conspecifics, or even the compressive forces generated by the animal's own musculature during extreme exertion. In Big AL's case, the presence of multiple healed rib fractures suggests either a single traumatic event that broke several ribs simultaneously, like a fall or a collision, or multiple separate incidents over the course of his life. Gastralia pathology. The gastralia, the belly ribs, a set of V-shaped bones that line the ventral surface of the torso in theropod dinosaurs, providing structural support for the abdomen and assisting in the mechanics of breathing, also show pathological changes in Big AL's skeleton. Gastralia are delicate bones that are easily damaged and that, because of their position on the ventral surface of the body, are vulnerable to injury whenever the animal falls or is struck from below. The pathological gastralia in Big AL's skeleton may represent compression injuries from falls or may be related to the same traumatic events that produced the rib fractures. Vertebral pathology. Some of Big AL's vertebrae show abnormal bone growth and evidence of degenerative changes that are consistent with either traumatic injury or the effects of chronic mechanical stress on the spinal column. The spine of a large bipedal theropod is a structure under constant mechanical stress. It must support the weight of the torso, the head, and the tail while allowing the flexibility needed for locomotion, feeding, and social interaction. Any weakness or damage in the vertebral column can produce cascading biomechanical effects that alter the animal's posture, gait, and overall physical capability. Metatarsal and phalangiopathology. The bones of the feet, in addition to the catastrophic osteomyelitis of the right foot that we have already discussed, show various pathological changes across both hind feet, including stress fractures, abnormal bone growth, and evidence of joint degeneration. The feet of a bipedal predator are subjected to enormous forces during locomotion. The entire body weight is concentrated through the hind feet at every step, and the impact forces during running are multiplied by velocity and by the dynamic loads of acceleration and deceleration. The accumulation of foot pathology in Big Al suggests that his feet were a chronic weak point, a constant source of mechanical vulnerability that limited his locomotor capability and that ultimately, through the osteomyelitis of the right foot, became the primary driver of his decline and death. Scapular pathology. The shoulder blade, the scapula, shows evidence of abnormal bone growth that may represent a healed fracture or a response to chronic soft tissue damage in the shoulder region. The forelimbs of Allosaurus, while not as dramatically reduced as those of the later tyrannosaurids, were still relatively short and were used in specific functional contexts, grasping prey during hunting, holding food during feeding, and possibly in intraspecific interactions. An injury to the shoulder region could have compromised the function of the forelimb on that side, reducing the animal's ability to hold and manipulate prey. When we consider all of these pathologies together, when we step back from the individual injuries and infections and look at the total picture, what emerges is the portrait of an animal in decline. Not a sudden, catastrophic decline like a fatal injury or an acute illness, but a slow, cumulative decline driven by the progressive accumulation of damage that the animal's body could not fully repair. Each individual pathology was survivable. Each individual injury or infection, in isolation, might have been manageable. The animal's resilience and healing ability were clearly substantial, as evidenced by the healed fractures and the survival through multiple separate traumatic events. But the cumulative effect of 19 separate pathological conditions, layered on top of each other, each drawing on the body's finite reserves of metabolic energy and immune capacity, was more than even a robust Allosaurus could sustain. The concept of cumulative pathological burden is an important one in both human and veterinary medicine. An individual with a single chronic condition can often compensate. The body adapts, reallocates resources, finds ways to function despite the limitation. But an individual with multiple chronic conditions faces a much more difficult challenge, because each condition draws on the same pool of physiological resources, and the interactions between conditions can create synergistic effects that are worse than the sum of their parts. A chronic bone infection in the foot reduces mobility. Reduced mobility reduces hunting success. Reduced hunting success reduces caloric intake. Reduced caloric intake impairs the immune system's ability to fight the bone infection. The bone infection worsens. Mobility is further reduced. And the cycle continues, spiraling downward toward a point from which recovery is no longer possible. Big Al appears to have been caught in exactly such a spiral. The foot infection, probably the most severe of his many conditions, compromised his hunting ability. His compromised hunting ability reduced his nutrition. His reduced nutrition impaired his ability to fight not just the foot infection but all of his other conditions as well. And the result was a progressive, inevitable decline that ended the life of a young predator who, in a more fortunate life, might have grown to full adult size and lived for decades as one of the apex predators of the Morrison Formation ecosystem. The age of Big Al at the time of death is estimated at approximately 7 to 8 years. A subadult, still in the rapid growth phase, still years away from reaching full adult size. The growth rate analysis conducted on his bones, based on the spacing and pattern of growth marks in the cortical bone tissue, indicates that he was growing normally for his age up until the last year or two of his life, when growth appears to have slowed or ceased. This growth disruption is consistent with the effects of chronic illness and malnutrition on skeletal development, and provides additional evidence that the final phase of Big Al's life was characterized by declining health and inadequate nutrition. 7 or 8 years old. Young. Strong, in potential if not in actuality. Full of the biological machinery needed to grow into a 9-meter, 2.5-ton apex predator. And yet dead. Killed not by a larger predator, not by a catastrophic accident, not by the dramatic geological or climatic events that periodically reshaped the Mesozoic world, but by the quiet, relentless, unglamorous processes of infection and malnutrition operating on a body that had accumulated too much damage to sustain itself. Big Al is a reminder that the lives of predators, even the most powerful and iconic predators, are not lives of unbroken dominance and effortless killing. They are lives of constant physical challenge, in which the predator's body is the instrument of its survival and in which any damage to that instrument can have cascading consequences that ultimately prove fatal. Big Al's body was his livelihood, and when that body failed him, slowly, incrementally, one pathology at a time, his livelihood failed with it. The Parasaurolophus walkeri holotype, the final case we examined in Part 1, deserves additional exploration for what it tells us about the hazards of the physical environment itself, the non-biological dangers that Mesozoic animals faced in their daily lives and that could, without warning, transform a healthy animal into a critically injured one. We discussed in Part 1 the hypothesis that the multiple traumatic injuries observed in this specimen, the fractured vertebrae, the broken ribs, the damage to limb elements, were most consistent with the impact of a falling tree. Let us examine this hypothesis more carefully and explore its implications for our understanding of the environmental hazards that dinosaurs navigated throughout their lives. The Cretaceous forests of what is now western North America were complex, multi-layered ecosystems populated by a diverse flora that included conifers, angiosperms, ferns, ginkgos, and cycads. Some of these trees reached substantial sizes. Cretaceous conifers, in particular, could grow to heights of 20 meters or more, with trunk diameters measured in meters. These were large, heavy structures that, like all trees, were subject to the forces of wind, gravity, water, disease, and mechanical failure. Trees fall in every forest on Earth, and they fall for a wide variety of reasons: windstorms, root failure, trunk rot, flooding that undermines root systems, the weight of accumulated snow or ice, lightning strikes, and the simple mechanical aging of wood that has been standing for decades or centuries. A large tree falling in a Cretaceous forest would have been a significant event. The impact energy of a tree 30 centimeters in diameter and 15 meters tall, falling from upright to horizontal, can be measured in thousands of joules, enough force to crush bone, rupture organs, and kill an animal outright if the tree lands directly on the body. An animal the size of a Parasaurolophus, 10 meters long, weighing perhaps 2 to 4 tons, would not have been small enough to be beneath the notice of a falling tree but also not large enough to be unaffected by one. A direct hit from a substantial falling trunk could easily produce the kind of multiple system trauma observed in the holotype. Simultaneous fractures of vertebrae, ribs, and limb bones, distributed along the dorsal and lateral aspects of the body in a pattern consistent with a blow delivered from above or from the side. The frequency of tree fall events in modern forests gives us a framework for estimating how common this hazard would have been in Cretaceous ecosystems. In modern temperate and tropical forests, the tree fall rate, measured as the number of trees that fall per unit area per unit time, varies from approximately 1 to 3% of standing trees per year in stable old-growth forests to much higher rates in forests subject to storms, drought, or other disturbance events. In a forest with a tree density of several hundred trees per hectare, even a 1% annual fall rate means that multiple trees are falling somewhere in the forest every year. For an animal moving through such a forest on a daily basis, feeding, socializing, and traveling, the cumulative probability of being in the wrong place at the wrong time when a tree falls is not negligible over the course of a lifetime. This is not a hazard that receives much attention in popular discussions of dinosaur paleontology. When we think about the dangers of the Mesozoic world, we tend to think about predators, about volcanoes, about the asteroid impact that ended the age of dinosaurs. We rarely think about trees falling on animals. And yet the physical evidence from the Parasaurolophus walkeri holotype suggests that this was a real and consequential hazard, a hazard that could cause severe, life-threatening injuries to large animals and that, like the parasites and infections we have discussed, operated outside the dramatic predator-prey framework that dominates popular understanding of the Mesozoic. The survival of the Parasaurolophus walkeri holotype after sustaining these injuries is, as we noted in Part 1, remarkable. The bone healing visible at the fracture sites indicates survival of weeks to months, a prolonged period of recovery during which the animal was carrying a burden of structural damage that would have been profoundly limiting. Multiple fractured vertebrae mean compromised spinal integrity, which means compromised posture, compromised locomotion, and compromised ability to perform the basic physical functions of daily life. Multiple fractured ribs mean compromised breathing mechanics. The rib cage provides the structural framework for the expansion and contraction of the lungs during ventilation, and fractures in the ribs can cause pain on every breath, reducing the depth and efficiency of ventilation and potentially leading to secondary respiratory complications. How did this animal manage? How did it breathe, move, feed, and avoid predators while carrying injuries that would challenge the survival of a modern large animal even with veterinary intervention? Part of the answer lies in the biology of bone repair in dinosaurs, which appears to have been robust and rapid by comparison with mammals. Studies of bone histology in various dinosaur species have suggested that bone formation rates in dinosaurs were generally high, comparable to, or in some cases exceeding, the rates seen in modern birds, which are themselves among the fastest bone-healing vertebrates. If Parasaurolophus could lay down new bone rapidly, the stabilization of fractures, while certainly not instantaneous, might have proceeded more quickly than it would in a mammal of equivalent size, potentially allowing the animal to regain some degree of function within weeks rather than the months that might be expected in a mammalian model. Part of the answer also lies in the social biology of hadrosaurs. If Parasaurolophus walkeri lived in herds, as the evidence from trackways, nesting sites, and bone beds strongly suggests, then an injured individual within a herd might have benefited from the protection and social support that herd membership provides. The presence of other herd members could have helped detect and deter predators, reducing the individual's vulnerability during its recovery period. The movement patterns of the herd might have brought the injured individual into contact with food and water resources that it could not have accessed on its own. And the social cohesion of the herd, whatever behavioral mechanisms maintained it, might have prevented the injured individual from being abandoned during its period of reduced mobility. This is speculative, of course. We cannot observe hadrosaur herd dynamics directly. But the inference is reasonable, based on what we know about the behavior of modern social herbivores in similar situations. Elephants, for example, are known to slow their pace for injured herd members, to maintain physical proximity to injured individuals, and to direct protective behavior toward vulnerable members of the group. If hadrosaurs exhibited similar behaviors, and there is no biological reason to assume they could not have, then the social environment of the herd could have played a significant role in enabling the survival of the Parasaurolophus walkeri holotype through its period of recovery. The holotype status of this specimen adds a layer of scientific and philosophical significance to its story. This is the individual upon which the entire species Parasaurolophus walkeri is founded. Every subsequent specimen assigned to this species is compared against this individual. Every anatomical description, every phylogenetic analysis, every ecological inference that refers to Parasaurolophus walkeri implicitly refers back to this particular animal, this particular skeleton, this particular set of bones that carry within them the record of a difficult and painful life. The definitional Parasaurolophus walkeri, the individual that represents the species to science, was a survivor of catastrophic trauma, an animal that persisted through adversity that would have destroyed a less resilient creature, and that carried the evidence of that adversity inscribed permanently in its bones. There is something almost literary about this, the idea that the representative individual, the archetype, the reference point for an entire species is not a pristine, idealized specimen but an animal marked by suffering and survival. It is as if the fossil record, in selecting this particular individual to serve as the foundation of Parasaurolophus walkeri's taxonomic identity, was making a statement about the nature of life itself, that life is not the pristine, unmarked ideal but the scarred, battered, imperfect reality of individual experience. As we draw the threads of this documentary together, let us step back from the individual cases and consider what the accumulated evidence tells us about the Mesozoic world as a whole. What kind of a world was it, really? What was the lived experience of being a dinosaur? The popular image of the Mesozoic, the image that has been shaped by decades of museum exhibits, children's books, documentaries, and franchise films, tends toward the spectacular and the dramatic. Giant predators stalking through primeval forests. Massive herds moving across volcanic landscapes. Aerial pterosaurs soaring above prehistoric seas. And all of this is real, all of this is supported by the fossil evidence. The Mesozoic was a world of extraordinary spectacle. But the cases we have examined in this documentary reveal another dimension of the Mesozoic, a dimension that is less spectacular but perhaps more truthful. A dimension of chronic pain, of slow decline, of individual animals struggling with the daily burdens of injury, infection, and disease in an environment that offered no reprieve and no medical intervention. A dimension in which the most common causes of suffering and death were not the dramatic predator-prey encounters of popular imagination but the quiet, grinding processes of biology. Bacteria colonizing wounds, parasites infecting blood, bones breaking and healing imperfectly, infections spreading through compromised immune systems. This is not a depressing picture. It is, if anything, an ennobling one. Because what the pathological evidence also reveals, in every single case we have examined, is resilience. Big John survived his horn wound for 6 months. The Brazilian Titanosaur carried its parasitic burden until the secondary infection finally overwhelmed its mobility. The Daspletosaurus healed from its facial bite wounds and continued to function as a predator. The oviraptorid parent maintained its brooding posture until the very end. The Edmontosaurus escaped a tyrannosaur and lived for months with a tooth in its tail. Big Al accumulated 19 pathologies and continued to try to hunt through all of them. The Parasaurolophus walkeri holotype survived multiple fractures that should have been fatal and recovered enough to resume at least some level of normal function. Every one of these animals, faced with circumstances that were trying to kill them, kept going. They kept breathing, kept moving, kept doing what living things do. And the evidence of that persistence, the healed bone, the remodeled tissue, the biological response to injury and infection that can only occur in a living, functioning organism, is preserved in their fossils with a clarity that allows us, across the immense gulf of geological time, to witness it and to be moved by it. The science of paleopathology, the study of disease and injury in ancient organisms, is a relatively young discipline within the broader field of paleontology, but it is growing rapidly in both its methodological sophistication and its interpretive power. The techniques that made the discoveries in this documentary possible, CT scanning, scanning electron microscopy, histological analysis, isotopic analysis, comparative veterinary pathology, are being applied to an increasing number of fossil specimens, and each new application reveals new stories, new details, new dimensions of the lives of ancient organisms that were previously invisible. We are learning, for example, that cancer was present in the Mesozoic, that malignant tumors have been identified in the bones of dinosaurs, including a hadrosaur from Alberta with a diagnosis of osteosarcoma, a bone cancer that is still one of the most dangerous and aggressive cancers in modern medicine. We are learning that dental disease was common in some dinosaur species, that tooth infections, abscesses, and jawbone pathology affected the feeding ability and overall health of animals across multiple dinosaur lineages. We are learning that arthritis, the degenerative joint disease that affects virtually all long-lived modern vertebrates, was also present in dinosaurs and that it could be severe enough to significantly impair locomotion and quality of life. Each of these discoveries adds another layer to our understanding of the Mesozoic world and another dimension to our appreciation of the animals that inhabited it. They were not simple creatures, not biological automatons operating in a world of straightforward ecological relationships. They were complex, vulnerable, individual organisms with bodies that could be damaged, that could be infected, that could suffer, and that could, within the limits of their biology, heal. The fossil record is not just a catalogue of species. It is a library of individual lives, each preserved imperfectly, each incomplete, but each containing, for those with the skill and patience to read it, the story of a creature that once existed, that once experienced the world, and that once, in its own way, struggled to survive. We began this documentary with a statement: they did not simply live and die. They bled. They suffered. They fought through agony that would have broken any creature without the raw, primal will to survive. After examining 7 cases of extraordinary pathology across the breadth of the Mesozoic, across multiple continents and multiple geological formations and multiple dinosaur lineages, that statement stands stronger than ever. The evidence is in the bones. The stories are written in stone. And the truth they tell, of a world of beauty and violence, of spectacle and suffering, of lives lived fully and fiercely and ended in ways that range from the dramatic to the heartbreakingly mundane, is a truth that enriches our understanding not only of the ancient past but of life itself. Because the lesson of the dinosaurs, the lesson that Big John teaches, that the Brazilian Titanosaur teaches, that Daspletosaurus and the oviraptorid parent and the Edmontosaurus and Big Al and Parasaurolophus walkeri all teach, each in their own way, is that life is not a guaranteed outcome. It is a constant negotiation between the organism and its environment, between the body and the world, between the will to continue and the forces that seek to end continuation. That negotiation never stops. It never becomes easy. And the dinosaurs, those magnificent, terrible, vulnerable, resilient animals, carried it on for over 160 million years across every continent on this planet, until the day the sky burned and the world they had built was taken from them in a geological instant. But before that day they lived. They lived with broken bones and infected wounds, with parasites in their blood and teeth in their tails, with the scars of combat on their skulls and the evidence of parental devotion preserved in their final postures. They lived fully, completely, in all the messy, painful, glorious complexity that the word implies. And the bones they left behind, the last physical traces of those lives, continue to tell their stories, to anyone who is willing to listen. The age of dinosaurs was not a simple time. It was as complex, as challenging, and as full of individual drama as any period in the history of life. The evidence is in the fossils. The stories are waiting to be read. And as our tools improve and our understanding deepens, more stories will emerge, more individual lives, more individual struggles, more examples of the extraordinary resilience and the equally extraordinary vulnerability of the animals that dominated this planet for longer than we can easily comprehend. Thank you for watching. Thank you for your attention, your curiosity, and your willingness to look beyond the popular image of the dinosaurs and to see them as they truly were, not as monsters or as attractions, but as living things, with all that implies. The bones remember. And now so do you. This concludes our documentary, When Dinosaurs Suffered Brutal Deaths, Hidden Diseases, and Survival Against All Odds. If you found this exploration meaningful, please share it with others who share your fascination with the deep history of life on Earth. Subscribe to the channel for future documentaries that will continue to explore the extraordinary stories hidden in the fossil record, stories of survival, of adaptation, of extinction, and of the endless, ancient, magnificent struggle of life to persist in a universe that is, at its most fundamental level, indifferent to whether it does or not. The dinosaurs persisted for 160 million years. Their story, preserved in stone, is one of the greatest stories ever told. And we are only beginning to read it.